filament structures of galaxies being pulled apart by the universe's expansion, with bubbles or voids forming in the gaps. Because of the universe's expansion, everything is moving away from everything. But of course, this isn't totally true in practice due to a mysterious force called gravity. Gravity is a pulling force, or technically, it is the curvature of space-time caused by uneven distribution of mass. On very small scales, gravity is hardly relevant at all. I don't feel any pull towards objects around me, only towards the Earth because it is so massive. Celestial objects close enough to the Sun are most influenced by its gravity, and all stars in the galaxy orbit around a supermassive black hole at the galaxy's core. But it doesn't stop there. You've probably heard that the Andromeda galaxy is hurtling towards us. How can that be when everything is moving apart? Gravity. Objects that are close enough together with a large enough mass are pulled towards each other by gravity faster than the universe can expand. This is why we have galaxy superclusters, and in fact we are part of one. Gravity is keeping these galaxy clusters bound together, meaning over extremely large timescales, collisions aren't totally unusual. In fact, a new theory has recently been proposed that the Milky Way may have recently experienced a collision with a large Magellanic Cloud-sized diffuse galaxy called Antlia 2. Scientists have discovered that the Milky Way has ripples consistent with it having had a collision in the past, but we couldn't pinpoint what it collided with until Gaia discovered the Antlia 2 galaxy hidden behind our galactic disk. This makes it very hard to spot, as although it is massive, it is very spread out due to the collision, and being behind our galactic disk makes it hard to see due to the stars and dust in the way. But that brings us on to the main topic of this episode, the Great Attractor. In an opposite vein from the supervoids video, where there are regions of space where there is an almost total absence of mass for hundreds of millions of light years in any direction, the Great Attractor is the biggest concentration of mass for hundreds of millions of light years. It is so massive that even though our galaxy is between 150 to 250 million light years away, we and all galaxies around it are currently moving towards it. Estimates put its mass at roughly 1,000 trillion suns, which is enough for many thousands of galaxies. But what could possibly be there that is that massive? Well, for the longest time, it was a total mystery, because, like Antlia 2, the region where the Great Attractor is located is hidden behind our galaxy's disk. However, X-ray telescopes can see through the disk, and recent technological improvements and advances in X-ray telescopes have meant that we have been able to detect thousands of galaxies in the region where the Great Attractor is supposed to be. But the mass detected didn't add up. There wasn't enough present to create such a pull. Further analysis has revealed something very interesting, that while we are being pulled towards the Great Attractor, there is something even more massive behind it, located 650 million light years away, called the Shapley Attractor or the Shapley Supercluster. Located there are many thousands of galaxies densely packed together with a mass of 10,000 trillion suns, and everything within 1 billion light years is being pulled towards it. On the other hand, looking the opposite direction from the Shapley Supercluster, we see an underdense region, where everything seems to be moving away from it, called the Dipole Repeller. It isn't actually repelling mass, but due to all the mass around it being pulled towards more dense regions by gravity, it creates the illusion that it is repelling that mass, although there are some scientists that do claim that an unknown repelling force is at work there. Simply put, we are still in very early days when it comes to understanding the universe. We do observe certain things, like the motion of galaxies, dense galaxy groups, and absences of galaxies in large voids or repelling regions. We observe the expansion of the universe and observe the filamentary structures. But the universe is an impossibly large place. We can only see so far, only live so long. Plus, our technology is limited. We have theories which try and explain what we see, but I really wouldn't be surprised to see these theories change as more data becomes accessible. Some may ask, what's the point then? However, I for one am hugely grateful for the bright minds working on this, as discovering our place in the universe is so fascinating. I'm glad humans have an insatiable need to explore and understand everything around them. This innate sense of wonder and curiosity is what drives the evolution of mankind, and I am excited to witness it. It takes teams of scientists with the right tools and software to track the stars and superstructures of our universe, but they're not the only things that are tough to manage. Ever feel that way about your business? Then you might need Odoo, today's sponsor. Odoo is an affordable, all-in-one platform with all the apps you need to run your business in one place. It has apps for everything, from accounting to website creation to inventory and much more. For example, its invoicing app is a super easy way to generate invoices by letting you add your customer, add products or services, and set quantities in just a few clicks. You can then send your invoice by email. Your customer can pay the invoice directly via the online portal, and the app allows you to track its payment status, whether it's pending, paid, or declined. Odoo offers a huge constellation of apps, and your first one is free forever with unlimited hosting and support. Looking to simplify the superstructure of your business? Just scan the QR code or click the link below and support the channel while you're at it. Movement through space is inevitable. You might not feel it, but right now you're sitting on a planet that is spinning on its axis, moving you at up to 1,600 kilometers per hour depending on your latitude. The Earth circles the Sun. The Sun moves through the Milky Way. The Milky Way moves through the local group of galaxies. And the local group moves through our local supercluster. And even that supercluster of galaxies is in motion, heading towards the Shapley supercluster, where scientists believe that there is a particularly large concentration of galaxies. I hope all this motion isn't making you too dizzy. But on the grandest scales of our universe, something strange is happening. Scientists have begun to realize that there is not enough mass in the Shapley supercluster to pull us towards it at the rate that we see. About 50% of the cause of that motion is unaccounted for. In 2017, researchers discovered a possible source for the rest of that motion. But it's not something pulling us, it's something pushing. I'm Alex McColgan and you're watching Astrum. Join with me today as we explore the evidence for the region of space known as the Dipole Repeller and try to understand how, in a universe filled with gravity, something can push us instead of pull. Let's start with a little context. It's taken a long time for astronomers to recognize that this motion was taking place. To understand that we were moving, scientists first had to make a map of the regions of space around us. And although we as a species have been mapping the stars since the beginnings of civilization, it was only thanks to Mr. Hubble in 1924 that we proved there are actually stars in other galaxies outside the Milky Way. Before then, although astronomers had seen fuzzy little clusters of light in the night sky that we now know to be galaxies, the common wisdom was that these were gas cloud spiral nebulae within the Milky Way, not something that existed beyond it. Hubble noticed several Cepheid stars, a type of variable star with a cycle of variation closely linked to their luminosity, within one such spiral nebula, and used the fact that this luminosity was very predictable based on distance to calculate very precisely how far away they were. Surprising many, he proved that they do exist beyond the Milky Way. Since then, astronomers have been scrambling to catch up with the new reality of galaxies and superclusters, and set about mapping the locations and distances to every galaxy they could find. Hubble had been studying Andromeda, our closest neighboring major galaxy, but there were others. By the 1970s, Stephen Gregory, Lard Thompson, and William Tift definitively proved that galaxies didn't just float randomly in space, but converged into superclusters, large filamentary or sheet-like structures that exist between large bubbles of void. They mapped the first supercluster, the Coma supercluster, which covered a region of space 100 million light years across. A whopping 95% of all galaxies are found in these superstructures. It wasn't until 2014 that our own supercluster, the Laniakea supercluster, was fully mapped. You might be surprised to hear it happened in that order. After all, wouldn't common sense say it's easier to map regions of space closer to us rather than ones further away? Why was it only nearly a century after the discovery of other galaxies existing, and 40 years after mapping the first supercluster, that we finally turned to our own? The answer is that mapping the local regions of space around us is surprisingly challenging, and it's all because of the Milky Way getting in the Milky Way. The Milky Way is full of gas and dust, and these regions are so difficult to penetrate that we can't really see beyond them. Towards the center of the Milky Way, this effect gets so bad that scientists have dubbed the whole area the zone of avoidance. Very little light gets through it. Not being able to see in this area is particularly relevant to our current discussion for reasons we'll get to later. In contrast to our local area, distant galaxies are easier to study, as all you have to do is point your telescope at a single point in the night sky and let it drink in the light. Mapping the area around us requires looking at every point in the night sky. It's proved quite difficult, although astronomers are now getting a better handle on it. Thanks to their efforts in looking at thousands of galaxies in our galactic neighborhood, and by studying galaxies' peculiar motion, or their motion relative to the cosmic background radiation that ignores the expansion of the universe, scientists have been able to group gravitationally bound galaxies into superclusters. At the center of our Laniakea supercluster lies a point known as the Great Attractor, an area 150 to 250 million light years away from us, that we, in the Milky Way, are slowly drifting towards. Sadly, the Great Attractor lies within the zone of avoidance, so it's tricky to see clearly what lies there. To confound things further, the Laniakea supercluster was also found to be moving. It travels towards another supercluster known as the Shapley supercluster, taking us along with it. At the center of this supercluster lies the Shapley Attractor, which also is believed to be incredibly dense in terms of mass. But frustratingly, this second attractor also lies in the zone of avoidance, making it difficult to see exactly what's going on over there too. Thankfully, as X-ray and infrared telescopes improved, it became possible to take a better look at these two attractors. But this is where the mystery begins. What mass is there is not quite massive enough to account for our apparent motion in that direction, which is why a team of researchers from the University of Hawaii published an article in Nature to attempt to explain this discrepancy. The team was made up of Yehuda Hoffman, Daniel Homerede, R. Brent Tully, and Helene M. Courtois. Together they created a new kind of map of the local universe around us. This time, instead of simply noting galaxies' positions, they highlighted their motions instead. This allowed them to create a map of flow lines, which, after mathematical analysis, allowed them to make assumptions about the locations of masses in our nearby superclusters. Their results were surprising. A lot of our local mass is moving towards the Shapley supercluster, which is what you would expect. But they also found a lot of mass is moving away from another specific region in space. They call this mystery patch of space the Dipole Repeller. Together, the Dipole Repeller and the Shapley Attractor both contribute about 50% to our motion, working together in tandem, hence the name dipole. But how? Gravity is a force that, so far as we have observed, only pulls. What lies in this region of space that allows a push to happen? Could it be a strange collection of white holes? The theoretical opposite of black holes that we've talked about in videos before? Or perhaps some source of anti-gravity? Not quite. The answer is nothing. The dipole repeller is a void, a bubble about 100 million light-years across that does not contain many, if any, major galaxies. It's one of the bubbles that exist between the filaments of the universe's structures. But interestingly, our galaxy's current motion lines up much more satisfyingly with the push from this region than it does from the pull of the Shapley attractor, which is a compelling argument in this theory's favor. So, how does nothing push? The answer is actually that this could be a pseudo-force more than it is a real one. Imagine a universe where all the galaxies were spaced equally. While the gravity of galaxies above would pull you, the gravity of galaxies below you would do the same. So would the pull of galaxies to your left and to your right. In this way, the varying forces of all these gravities would balance each other, leaving you to not really travel in any direction. You'd be in a perfect equilibrium. But what would happen if we removed the galaxies from one of these directions? What would happen if we added a void? Well, then the scales would tip. There would be one direction that no longer pulled you, leaving the opposite direction's pull to act on you unimpeded. As a result, you would move away from the void as if it were pushing you. Everything near a void will thus move away from it, making it seem to have a repelling gravitational force. It is something of an optical illusion. There is another explanation for why a void space might push you, which might work in tandem with the pseudo-force. The universe is expanding, and that expansion shows no sign of slowing down. In fact, it seems to be speeding up. However, this expansion is counteracted by gravity, and in areas where there is more gravity, less expansion seems to take place. Stars aren't just being pushed away from each other, they're also being pulled together. Conversely, in a void, there is nothing to contain this rampant expansion. As a result, void spaces literally will swell compared to their supercluster counterparts. It might be done by warping the fabric of reality, but this also achieves a sort of push. Since 2017, not much more has come to light about the existence of the dipole repeller. As this is still an expanding field of research, there's some debate about whether it's really there, or how influential it might be on our galaxy's current motion. It is difficult to observe due to the Milky Way's obscuring effect, and there's always a challenge inherent in trying to spot the absence of a thing rather than its presence. However, Tully and his fellow researchers hope that with the aid of future ultra-sensitive surveys in multiple spectrums of light, it will be possible to map out the few galaxies that lie in this void, and generally confirm its existence in the region they hypothesize. We are constantly moving through space, but even the science of space is always in motion. Each new galaxy, along with data regarding its redshift and travel speed, helps us develop a broader understanding of the movement of the galaxy. It's fascinating to think that not all of that motion is caused by the pull of gravity. It might turn out that sometimes the universe just needs a little push to get going.
You may or may not have come across the name Boötes void in the past, described as one of the biggest voids in space that we know of. But what does that really mean? First things first, it is not this image. If you Google Boötes void, this image comes up a lot, but this is actually the molecular cloud Barnard 68, a cloud of dust in space that doesn't allow light from stars behind it to pass through, which I suppose makes it look like a void in space, but it's not in reality. To understand what Boötes void really is, we need to understand some context. We know that space exists outside of Earth, but even outside of Earth's atmosphere, space is quite populated, and astronomically speaking, you are spitting distance from other objects like the moon, asteroids, other planets, and the sun. You can still reasonably use kilometers or miles to measure distances at this point. Outside of the solar system, objects begin to get a bit further away. We start to measure in light years at these distances, a light year being 9.46 trillion kilometers. At this scale, we can see that there are plenty of stars in the near vicinity to us. All the stars in our galaxy make up the Milky Way galaxy, a large structure roughly 150,000 light years across. Beyond the Milky Way are more galaxies, the closest big one being Andromeda at 2 million light years away. Beyond that, we see the local area of galaxies that we are part of. What I want you to pay most attention to at this point is the clustering and banding of these galaxies. You'll see that they aren't evenly distributed. In between all these galaxy groups are voids, where there are only a few galaxies dotted around the place. These are just small voids, being only tens of millions of light years across. Zooming out once more, we start to see this banding happening on a grand scale. At these kind of distances, we begin to see that the universe tends to have a kind of web or filament structure made of galaxies. In between these huge clusters and filaments stretching for hundreds of millions of light years are supervoids, one of the biggest that we know of being the Boötes void. At 330 million light years across, a typical region of space would find about 2,000 galaxies within that volume on average. But this doesn't mean there is absolutely nothing there right now. We have discovered a very thin filament of about 60 galaxies in this void. But they are so sparsely distributed that if the Milky Way was in the middle of Boötes void, we wouldn't have known other galaxies existed until the 1960s due to the distances. So, there you have it. That's what Boötes void really is. A very empty patch of space, hundreds of millions of light years across, containing some very lonely galaxies.
Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.
Gerard 't Hooft won the Nobel Prize in 1999 and the recent Breakthrough Prize for his work on the standard model of particle physics. He also thinks that quantum mechanics is nonsense. Indeed, he has an alternative theory for quantum mechanics that he says is how the world really works. This theory has been almost entirely ignored by physicists, which is unfortunate because he predicts a limit for what quantum computers can do. Today I want to tell you about 't Hooft's ideas about quantum physics to the extent that I understand them. I learned this from a book he's written called The Cellular Automaton Interpretation of Quantum Mechanics. In his own words, the subject of this book is the reality behind quantum mechanics. But the book isn't just about quantum mechanics, because this new reality would then be the basis of all of physics. As 't Hooft puts it, what we are really after is a new approach towards guessing what the theory of the world is. Let's start with a quick reminder of how quantum mechanics normally works. We're used to objects having definite properties that you can quantify. This desk is white, this chair is solid, and this sentence makes sense so far. In quantum mechanics, it doesn't work like that. Instead, everything is described by a wave function. It's usually denoted by the capital Greek letter psi. Basically, quantum mechanics is all about big size. The wave function describes the state of a system. The system could be, for example, the particle, and the state could be its position. But then the wave function usually doesn't tell you exactly what the particle's doing or where it is. It just gives you a probability that you can calculate from the wave function. The wave function might tell you, for example, that the particle has a 50% probability, say, being on the left side of the screen and a 50% probability of being on the right side. Then if you measure the particle, you know it's, say, left with 100% probability. But the probability came from the wave function. So that means if you make a measurement, you need to update the wave function to reflect the change in probability. This is called the collapse of the wave function, or the reduction, or the update. The issue is that this collapse isn't local. It doesn't start at one place and then spreads from there. It happens at one instant everywhere, faster than the speed of light. That the collapse of the wave function breaks the speed of light limit is why Einstein didn't like quantum mechanics. I think Einstein was right, and 't Hooft thinks so too. The way that 't Hooft wants to improve quantum physics is by doing away with the collapse of the wave function, and he does that by getting rid of free will, by making quantum mechanics entirely deterministic. In its current version, quantum mechanics isn't deterministic because the wave function only gives you probabilities. It doesn't determine the result of a measurement. In 't Hooft's version, it does. It's just that we can't predict the result because we lack information. That is, 't Hooft says that the randomness of quantum mechanics has the same origin as any other randomness we observe. Like when you say, throw a die. It's not that the outcome of the throw wasn't determined. We just can't calculate it because we don't know the exact initial state. This again is also what Einstein thought, and why he said God does not play dice. Okay, so 't Hooft wants to return us to determinism, but what does free will have to do with that? For one thing, philosophers have debated for a few thousand years whether determinism is compatible with free will, so quite possibly just the act of returning to determinism upsets some people's ideas of free will. Then again, most philosophers also agree that the indeterminism of quantum mechanics doesn't give you free will either. So basically, it doesn't matter. Free will doesn't make sense whether or not quantum mechanics has a deterministic root. But this somewhat philosophical question actually isn't why 't Hooft is talking about free will. He talks about this because some notion of free will is an assumption for the most famous proof that quantum mechanics are supposedly correct. This famous proof is what received the Nobel Prize in 2022. And yes, I'm talking about tests of Bell's theorem. Bell's theorem says that a deterministic theory, which is local, so what 't Hooft wants, will, given certain extra assumptions, obey an inequality for the correlations between certain measurement results. Experiments violate this inequality, hence the vast majority of physicists conclude a deterministic and local theory can't explain our observations. But 't Hooft says the problem is the extra assumptions to Bell's theorem, one of which is that the experimenters can freely choose what they will measure. And that is where free will comes in. 't Hooft points out that in a fully deterministic theory, whatever the experimenter chooses was also determined. Everything that has happened, does happen, and will happen was already encoded in the initial conditions at the Big Bang. If you weren't around at the Big Bang, that's a shame. It was quite the event. But don't worry, you don't need to know what happened. It only matters that this information exists because that explains why the measurement outcome always fits to the measurement settings. 't Hooft is very unapologetic about his dismissal of free will. He writes, like it or not, the experimenter's actions are determined by laws of physics. Their decisions logically have their roots in the distant past, going back all the way to the Big Bang. But what does this mean? What exactly was determined? What was determined is that the experiment and the system that you were looking at must be correlated with what you measure, and these correlations must have been present already in the initial state of the universe. About this, 't Hooft writes, it clearly is a mysterious correlation, but it is not at odds with what we know about the laws of physics. This is the important point of 't Hooft's proposal and what has sometimes been called superdeterminism, that the decision of what you measure is correlated with the state of the system that you measure. It's not a causation. It's not that the wave function of an electron makes a particle physicist turn a knob. It's just that the laws of nature are so that the two things must always fit together. 't Hooft also thinks that the issue of free will in quantum mechanics is somewhat of a red herring, because what we're really talking about is just a mathematical model that helps us make predictions. As he writes, the notion of free will must be replaced with the notion that a useful model of nature should give correct predictions. Somewhat more technically, 't Hooft says the following: the wave function that we use in quantum mechanics is all well and good to describe what's going on, but it isn't real. There is, however, a different wave function which is real. He calls it ontological, and that wave function is one which always gives 100% probability of getting a particular measurement result. In particular, the states that we think of as classical non-quantum are ontological. They're real. A dead cat is real and a live cat is real, but a dead and a live cat isn't real in 't Hooft's framework. So he doesn't say that the quantum mechanics we currently use is wrong, it's just that we interpret it the wrong way. When we set up an experiment and we write down the wave function for it, then this wave function does not describe the actual real state of the system. It describes the probabilities that the real state could be because we lack information. And this all sounds very nice and reasonable, but the price you have to pay is that you need this correlation between the thing that you're going to measure and what you measure about it. 't Hooft's book is called The Cellular Automaton Interpretation of Quantum Mechanics, but I haven't said anything about cellular automata, so what is this about? Cellular automata are what 't Hooft thinks makes up the deterministic basis behind quantum physics. A cellular automaton is a compact, so localized object that proceeds in discrete time steps. A cellular automaton can interact with its neighbors, and we know that this can give rise to surprisingly complex emergent features. Stephen Wolfram, whose theory of everything we've talked about in the previous video, also uses a version of cellular automata. For 't Hooft, the relevant thing is that the cellular automata only interact with their neighbors. They have what we call a nearest neighbor interaction direction. This matters for 't Hooft's purposes because remember, we want to have a local theory, no faster than light stuff going on. 't Hooft's cellular automata are basically quantum versions of gears. He thinks that something like this is what the universe is ultimately made up of in extremely tiny versions at the Planck scale. Imagine a screen displaying the evolution of our cellular automaton. We imagine its pixels to have roughly the size of one Planck length, 10 to the minus 33 centimeters. So the cellular automata are ridiculously tiny and they combine together to give rise to what we call particles and presumably space itself. And because he thinks that the ultimate nature of reality has something to do with the Planck scale, he also thinks that quantum computers will eventually run out of steam. This is because they must make do with these ontological states in the cellular automaton, and these are far fewer states than physicists currently believe are real. He writes, factoring a number with millions of digits into its prime factors will not be possible. If engineers ever succeed in making such quantum computers, it seems to me that the cellular automaton theory is falsified. If you've already forgotten half of what I said, this video comes with a quiz that lets you check how much you remember. Okay, so that's what 't Hooft says. Now, let me tell you what I think about this. First of all, I think that he's mixing together two different ideas. One is this idea with the ontological states and how to formulate a local and deterministic theory that underlies quantum physics. The other is the stuff with the cellular automata. I'm not super excited about the cellular automata because anything discrete, be that in space or in time, will violate the symmetries of Einstein's theories, and it's very difficult to make that work without being crudely in conflict with data already. 't Hooft knows this, of course, but I think the problem is more serious than he makes it sound. That discrete cellular automata have this problem with the symmetries of Einstein's theories is why I believe Stephen Wolfram began using these hypergraphs. These have a much more difficult update rule than steps in time, and they're compatible with Einstein's theories. Now about 't Hooft's idea for the ontological states. Yes, I think you can do it, but in all honesty, I don't see the practical use, because he doesn't explain what the ontological states are or how you could ever figure out what they are, and without that, you can't do anything with this idea. Now look, what I just said may be wrong, and maybe he solved a big problem, it's just that we're all too stupid to understand it, but on a practical level, I don't know what to do with this interpretation. Be that as it may, I think this is a very interesting proposal. At the very least, it's a fresh perspective on an old problem. It's also somewhat of a sad story because 't Hooft's ideas about quantum physics have been ignored by almost all physicists. You'd think that someone with as many credentials as 't Hooft would have a chance that his ideas be taken seriously, but evidently not. So what do you think about this? Does 't Hooft's idea make more sense than quantum physics, or are they both equally incomprehensible? Let me know in the comments. Yes, I've been talking about quantum mechanics again. Did you know that I have a course on quantum mechanics that you can take for free on Brilliant? My course will help you understand what a wave function is and what the difference is between superpositions and entanglement. It also covers interference, the uncertainty principle, and Bell's theorem. And after that, you can continue maybe with their course on quantum computing or differential equations. Brilliant offers courses on a large variety of topics in science, computer science, and mathematics. All their courses have interactive visualizations and come with follow-up questions. Whether you want to know more about large language models or algebra, want to learn coding in Python, or know how computer memory works, Brilliant has you covered. It's a fast and easy way to learn, and you can do it whenever and wherever you have the time. And they're adding new courses each month. And of course, I have a special offer for viewers of this channel. If you use my link brilliant.org/Sabina or scan the QR code, you'll get to try out everything Brilliant has to offer for a full 30 days, and you'll get 20% off the annual premium subscription. So go and check this out.
Not so long ago, we discussed the idea behind alchemy, or I guess technically, cosmological alchemy. Basically, the ability of the universe to create gold from lighter elements, for example, iron. And in that video, we discussed a somewhat recent explanation for how a very bizarre, very powerful emission in 2004 seems to have produced a huge amount of gold through a very powerful flare around a magnetar. In this case, it produced approximately 1 Mars worth of gold, or by mass, approximately 1/10 of planet Earth. But in this video, we're actually going to discuss a slightly different type of this alchemy that happened right here on planet Earth, inside what's known as Alice detector, a detector used by CERN in its extremely powerful particle collider. And so in this video, let's discuss this particular study you can find in the description, where researchers part of the Alice collaboration discovered a completely new way gold seems to be generated inside various particle colliders. And in this case, from lead, which by itself is actually kind of symbolic and kind of important. But just for funsies, let's briefly discuss alchemy and its history, and specifically the concept known as chrysopoeia, from ancient Greek for gold making, with the image of Ouroboros right here, used by ancient alchemists to represent this idea. And although technically alchemists pursued many different goals, one of the main goals, especially for some of the latest alchemists, was to try to create gold or silver from other metals, usually lead. And specifically because lead and gold actually do have very similar density, and so a lot of ancient alchemists assumed that it should not be too difficult to turn one into the other. And technically they've been trying to do this for nearly 1500 years. For example, this particular idea was initially described back in 3rd century AD, initially described by Cleopatra the alchemist, not to be confused with Cleopatra from Egypt. And so this Greek alchemist was one of the first to propose that it should be possible to convert stuff into gold by using specific alchemical processes. And so by 16th and 17th century, alchemists developed a lot of advanced techniques, with many of them serving as a basis for future science, specifically medicine and chemistry. And that's because in the process they were also able to create things like pigments and certain chemical substances. But they were never able to reach the dream of chrysopoeia. The lead was never transmuted into gold. And for one simple reason. Back then we still had no idea gold and lead were completely different elements with entirely different number of protons and neutrons. Naturally because the periodic table would not exist for another 200 years. But in the last few decades, this idea came much closer to fruition. Or basically, by using science, researchers were actually able to transmute one thing to another. Obviously not through alchemy, through the process of nucleosynthesis. And one of the first and most well-known attempts was back in the early 1980s, specifically March of 1981. Back then, scientists from the Lawrence Berkeley National Laboratory in California definitively found a way to convert bismuth into gold. In this case, bismuth and gold are extremely close to each other on the periodic table. And so here, through the process of particle collision, they were able to remove 4 protons from bismuth in order to produce gold. But because these were powerful collisions, they also removed a bunch of neutrons, usually anywhere from 6 to 15. And this actually created a bunch of different gold isotopes, including some that were radioactive. And that's exactly how they were able to confirm that gold was present. Even though the amount of gold was extremely small, by detecting radiation coming from unstable gold nuclei, they were able to confirm that gold was indeed there, and was actually decaying for at least 1 year. But because of the way it was produced, some of these gold atoms were also stable and were extremely similar to your typical gold we usually use in jewelry. But obviously this was not a cheap process. Here, a single hour of the experiment was at least $5,000, which means that by using this method to create 1 ounce, it would probably cost over $1 quadrillion in total. Even though the gold is pretty expensive today, over 3,000 US per ounce, it's not quadrillion. So yeah, not a very efficient way. But this was using bismuth and not lead. And that's because generally bismuth is just a little bit easier to separate from gold because it's generally a much more homogeneous element. The lead though has proven to be so much challenging. And so basically trying to turn lead into gold apparently is not as easy. But in this new study, researchers discovered an intriguing new method. A method that has actually turned a load of lead into gold in many different particle colliders through a process that we didn't know about before. With this new study measuring the transmutation of lead into gold that apparently has been happening inside the Large Hadron Collider for many, many years. Now normally in a typical collider, the main purpose is to visually collide atoms, or to create these powerful collisions that then form quark-gluon plasma, representing an extremely hot and very dense state of matter, somewhat similar to what the universe was like in the first millionth of a second. But these collisions are not very frequent, and a much more likely result is a near miss, where essentially two atoms passing very close but not really touching, just interacting through other means. And apparently when this happens, because these atoms are moving super fast, and also because many of them contain a lot of protons which produce electromagnetic fields, this in theory can actually induce a type of an electromagnetic interaction as these two atoms pass close enough. In some sense you can imagine this as basically two magnets moving very close to each other at ridiculously high speeds. But for atoms of lead, their electromagnetic field is particularly strong. Here lead contains 82 protons, which produce quite a powerful elementary charge. Moreover, at very high velocities of 99.99993% of the speed of light, as they move across from each other, because of the Einsteinian principles, instead of having magnetic lines around the atom, here relativistic effects force the electromagnetic field to become a kind of an extremely thin, pancake-like object. Which means that when these two atoms pass close to each other, it's sort of like having two pancakes smack each other at a very high velocity. And turns out that this produces a very short-lived pulse of photons, which can then influence one of the atoms. This triggers a process known as electromagnetic dissociation. And here these photons can interact with anything, but sometimes they interact with the nucleus, which very often causes the oscillation of the structure, resulting in the ejection of a small number of neutrons or protons. And sometimes these 82 protons become 79 protons. And so basically when 3 protons escape, lead becomes gold. And so based on this theory, researchers decided to analyze approximately 3 years of observations from Large Hadron Collider, discovering that it indeed produced quite a lot of heavy stuff. And you can see some of it right here. There was quite a lot of thallium, quite a lot of mercury, but the third most common element was gold, with some other stuff visible in this image. And according to the calculations, gold seems to be produced at a rate of about 89,000 nuclei per second during a typical run inside Large Hadron Collider. And once again, all this was just the result of these lead-lead collisions, or near collisions, inside the particle accelerator. And so during Run 2, which lasted for 3 years between 2015 and 2018, this resulted in a production of 86 billion gold nuclei, or approximately 29 picograms. So yeah, still quite expensive and very inefficient, but technically this was transmutation after all. And except that for alchemists, they were trying to get rich. Yeah, this would not work in this case. Moreover, all these atoms only lasted for a fraction of a second, mostly because they usually collided with something afterwards, fragmenting into protons, neutrons, and other particles. And that's actually how scientists were able to detect them. By detecting collisions inside the 0-degree calorimeter, they were able to count the number of gold nuclei destroyed inside the accelerator. And so basically extracting this gold would also be out of the question. But for science though, this is still a pretty cool discovery. It basically confirms that atoms can transmute just through these electromagnetic interactions, especially if they're moving really fast. And for particle accelerators and for particle physicists, this allows them to recalibrate certain particle colliders in order to reduce energetic losses and to improve future performance. And so the idea proposed by Cleopatra the alchemist approximately 1700 years ago has now been officially put to practice. Maybe not in the same way as she described, or maybe she was onto something after all. Because I mean, if you squint your eyes here and sort of ignore the fact that this is a snake, also known as Ouroboros, what if she was actually describing a particle accelerator? Oh my god, I just discovered some kind of a conspiracy theory, didn't I? On that note, don't tell Joe Rogan because I'm sure he's going to invite a bunch of people to talk about this, and we'll definitely come back and talk more about these ideas of transmutation, or technically nucleosynthesis, as scientists discover more, especially by looking around the universe. On that note, check out the previous video in the description. Thank you for watching, subscribe, support the channel on Patreon by joining the channel membership, or by buying the 1% t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye-bye.
Nice. Nice. Så der er Tyrone. Hvem er det? Oh my god. Jeg kigger bare væk et sekund, man. Og så er de skåret i bare. Og de er bare vilde. Victoria. Ja. Nu giver Victoria skylden her i byen. Hun rydder ikke op.
Adventure Time is a children's cartoon full of adult life lessons, which you might have missed while you were young. There's so many great and detailed themes like heartbreak, grief, personal growth, but there's also this very emotional topic of identity struggles throughout the series. We see this in the greatest hero of Ooh, Billy, struggling with what it means to be a hero. We see it through Finn, becoming obsessed with every girl he meets, but we also see this through Fern in a very tragic way. I've always seen Fern's story as the painful embodiment of growth through rejection, crisis, and transformation. It taught me that becoming yourself isn't always about knowing who you are, but surviving and discovering who you're meant to be. And if you follow his story to the end, you might just find a piece of yourself in him, too. Fern's path doesn't start by being born with a purpose. He was born by accident, something that should have never happened. Adventure Time's main hero, Finn, once had a sword made from a version of himself. Literally, it first appeared in Breezy, where Finn awakens to Breezy's final song. However, instead of seeing Breezy in her queen form, he has a vision of Princess Bubblegum holding some weird sword we hadn't seen before. Now later in the episode Is That You?, after a multiverse mishap, a copy of Finn's consciousness got trapped inside a blade. That blade became known as the Finn sword, the one Princess Bubblegum was holding. It talked like him, thought like him, it was him, in a way, a piece of his soul made of steel. And that sword is a piece of himself that Finn would lose, like, totally by accident.
Hello.
It's the boy. I'm a boy.
Get a new sword. Luckily, Finn also acquired a different weapon, a cursed magical plant called the grass sword.
Here you go. A grass sword. It's a bargain.
It was beautiful, deadly, and a little too perfect. it cuts a tag effortlessly in the shape of Finn's face, foreshadowing what the sword would become later.
Something is terribly wrong with that awful sword.
It was alive, and it wanted something, so it started wrapping itself around Finn's arm.
Dude. Yeah.
And it wasn't coming off. Finn and Jake tried to find the grassy wizard again to lift the purse from the sword.
Lift the purse.
But he wasn't really digging it.
You have no power over me, young fool. The grass sword will be part of you for all eternity.
But after accepting that the sword would be a part of Finn, it retracted and became something Finn could control.
Now that you've accepted it, you can control it.
Eventually, Finn would lose that arm, as I've previously covered in a different video. Not to bore you with details, but Finn later regrows his arm with a small thorn in his hand, a remnant of the grass sword that would only activate when Finn is in a life-threatening crisis. And such a crisis was just about to happen 2 seasons later. In the episode I Am Sword, the one where we saw Finn throwing his Finn sword away, Finn has a nightmare of being a girl thief and robbing a man in the woods. When he wakes up screaming, he runs downstairs to find Jake and tell him about his dream. Jake tells him that it was probably just a guilt dream, but the dreams persist, and Finn eventually realizes that the sword is in trouble. It's trying to reach him. So the duo travels to the spiky village, where the bandit princess is still using the sword for all the wrong reasons.
OMG, you ruined my life, bandit princess. Mine too. You trashed my hero streak.
Once they found her, they fight, and in the chaos, the grass sword activates, sprouting from Finn's palm to save his life, but accidentally stabs the crystal heart of the Finn sword and shatters it. But it isn't until the episode Reboot that the fusion truly begins. The grass sword separates from Finn's body again, just like it did in the Citadel. But this time, it finds something else to cling to, something fractured, something vulnerable. The broken remains of the Finn sword. Inside that blade, the tiny version of Finn, still alive, still trapped, met the grass demon, the twisted parasite that powered the grass sword. And together, they fused. Not with some magic, not with love, but with confusion, possession, and a deep need to escape. What emerged wasn't just a new sword, it was someone, a bundle of cursed grass, twitching with electricity, shaping itself into a boy. He stands up slowly, unsure of what he is, but absolutely certain of who.
Also, why are you dressed like me? Get a life, man. What?
He has the voice, the memories, the instincts.
Where do you want to go?
But something's off. It's like watching a memory walk around wearing someone else's skin. This is how Fern is born. Not from parents, not from purpose, but from a broken version of someone else, cursed and left behind. And from the very beginning, all he wants is to be seen. Not as a copy, not as a monster, just as a real person. He's a textbook case of identity fragmentation. He wakes up with memories that aren't his, emotions he's never earned, and instincts that were shaped by someone else's pain. He's living in a body made from violence, animated by trauma, and wrapped in vines that seem to protect him, but mostly just keep him bound. And that's the trap, because the vines aren't just his body, they're a symbol of something deeper. Expectations, inherited roles, someone else's story tightening around you like roots. And maybe you felt that too, like you were following a script that was handed to you, playing a part that never really fit. You try to say the right things, act the way you're supposed to, but deep down, it never feels natural. It's not that you don't belong, it's that no one ever asked who you really are. And that's the quiet truth Fern teaches us early on, that becoming yourself isn't just about knowing who you are, it's about untangling who you were told to be.
Why don't you set him straight and tell him who the real Finn is?
That one?
What?
Yeah, I don't know what you are.
But little did we know, Fern, or Grass Finn as he's still called at this point, was about to show us that he was more Finn than Finn would ever be. If you draw a parallel, you can see some common ground. Fern is Finn from the early seasons. The young, reckless boy who charges into battle with no plan, only fists and bravado. Except, Finn grew up. Fern didn't. Even though he has the same memories, he never lived through them. He remembers losing friends, but not what it felt like. He remembers hugging Jake, but not why it mattered. He remembers growing up, but never actually did. He looks real, but he's hollow in all the places Finn filled with love and pain. And that gap, the gap between memory and maturity, is where Fern begins to unravel. When Fern goes back to the tree fort, it's not as a villain, it's as someone going home. He opens the door and walks inside. But the first person he meets isn't Jake, it's Bimo, a tiny robot and one of Finn's oldest friends. And Bimo is terrified, so he hides. Fern tries to feel out the space. He sniffs the air, touches some objects. He reaches for nostalgia, for belonging. That's when Finn finds the scrapbook. It's filled with drawings, photos, and mementos, pieces of a life he remembers living. He flips through page after page, expecting something to click.
That was when Bimo lost control of the tank.
But instead of clarity, he finds contradiction. The life he remembers already belongs to someone else. Someone still alive. Someone everyone else seems to prefer. Someone with skin made out of flesh, not out of grass. And that realization that he's just the second version of someone better hurts more than anything. So he starts tearing the tree fort apart. Not out of malice, but confusion, frustration, grief. When the real Finn and Jake come home, they find their fort in ruins. Jake's furious, Bemo's scared, and Fern is crumbling. But Finn doesn't attack him. He sees the sadness in Fern's eyes, and he does something small but meaningful. He offers Fern a Finn cake, a silly little dessert that's always been for Finn only. But in that moment, it's more than just a sugary treat. It's an invitation. It's a way of saying, you don't need to be me to belong here. And for the first time since waking up, Fern smiles.
Maybe I'm not who I am.
Just a little, but it's real. That night, they all sleep at the treehouse. Finn, Jake, and Bemo inside, with Fern on the roof. Not quite family, not quite stranger. Something in between, something growing. But growth is rarely peaceful, and Fern's roots are tangled. The next day, Finn leaves Jake to spend time alone with Fern, to treat him like a brother, like a second chance. Jake tries. He cooks for Fern, he plays music with him, he even suggests they smash monsters together. But Fern's body doesn't work like Finn's. He can't eat, he can't breathe, so he can't even play the flute. He has all of Finn's memories, but none of the humanity. And that's when the loneliness sets in. Not because he's isolated, but because no one sees him as real, not even the world around him. When Fern and Jake go find the grassy wizard, the one who originally created the grass sword, Fern finally asks the question that's been eating away at him.
Why did you make me? Am I bad? Am I part of a conspiracy?
And the answer?
I just thought it would be cool. Grass blade. It's a sort of pun.
There's no prophecy, no plan, not even an accident. Just a joke. Just a weapon. Fern was never meant to be anything at all. But Fern refuses to believe that. It can't be. Not really. He knocks the wizard out cold. Not to kill him, but to stop the hurt. To reject the idea that he was never meant to be. And when Finn returns, he praises Fern's choice. Tells him he did good, that he was brave. Fern looks at him, this boy whose life he remembers, whose face he shares, and decides, finally, to be someone new.
Good job, Grassme.
But I'm not you. It's clear that I'm someone else.
From that moment, he also calls himself Fern, and then steals a motorcycle and drives off into the dark. Fern's life started by showing that even if you've just been told you were never meant to exist, you still get to decide who you'll become. And that's only the beginning for Fern. He may have picked a name, but that doesn't mean he found peace or identity yet. In fact, naming himself Fern the Human only made the silence louder. Because saying, I am someone, doesn't change how the world looks at you. And no matter where Fern goes, he still sees it in their eyes. Doubt, distance, fear. Now, after Finn was about to leave on his journey to the islands, he wanted Fern to fill in for him.
I might be gone for a while on this trip, see? And I need someone to, cover for me, here and new.
And he tried. He tried to slay monsters, save people, do good. But it never feels right. Everything he does just wasn't enough. It feels like a performance.
The dude who dinks it up. Just like I dinked it up when you left U. I was supposed to protect it. Instead, it went all crazy. I didn't even help.
And deep down, he knows he's still living in someone else's shadow. In Whispers, we start to see the cracks take over. Fern becomes more withdrawn, more erratic.
Don't trust me to guard anything. I'm a total scrub-up.
He starts watching Finn from a distance, studying him. Not as a brother, but as a rival. Because no matter what Fern does, Finn keeps being chosen. Chosen to lead, to protect, to be remembered. And what hurts most? Fern remembers all the same things. He feels them in his roots. But no one treats him like they're his. Eventually, Fern finds something dangerous. He can disguise himself. He learns how to cloak his grass body and appear identical to Finn. And that's when the idea forms.
It doesn't matter how hard I try. I'll always just be in the shadow of the real Finn. Unless I could become the only Finn.
If he can't live as Fern, then maybe he'll just replace Finn. By the time we reach 3 buckets, Fern's jealousy has festered into something harder. He doesn't just want to be seen, he wants the world to forget Finn ever existed. He lures Finn into a trap, locks him behind a stone door, and declares,
It's been your home long enough. It's Fern's turn. I think I'm gonna be a really great Finn.
It's saddening. Not because Fern is cruel per se, but because he truly believes that this is the only way forward. When the world tells you you're not enough, eventually you start to believe it. And if you believe it long enough, you'll do anything to change it. It doesn't last long though. Finn escapes, the two fight. It's fast, clumsy, desperate. Not 2 heroes, 2 brothers. 2 scared kids trying to prove they deserve to exist. And then, by accident, just one misinterpreted voice command, and Finn cuts Fern to pieces. There's no triumph in his face, no relief, just horror. Because Fern may have gone too far, but he was never a monster. He was just lost. And here we truly get to see how far Finn has come. Like I mentioned earlier, Finn used to be that kid running around willing to kill everything he's deemed as evil. But now there's more to it. There's the complete moral question attached to what makes someone evil. Fern tried to get rid of Finn, and yet Finn realizes it's not completely his fault. And as Fern lies in a heap of shredded vines and scattered memory, something inside him still clings to life. A small, twitching eye, still moving. Fern isn't gone. Not yet. But what grows from here won't be the same. Fern's story could have ended in that pile of broken vines. It might have been a tragedy, short, confusing, unfinished. But instead, it becomes something worse. In the episode 17, Fern returns, not as himself, but as something new. He crashes Finn's birthday party in full armor, silent, powerful, unfamiliar. He doesn't announce who he is, he just challenges Finn. And when Finn defeats him in an arm wrestling match, the helmet finally comes off. It's Fern, but not really. His body has been restored, refined, sharpened into a weapon. And the one responsible? Princess Bubblegum's uncle, Uncle Gumbald. The same Gumbald who is quietly assembling an army, preparing for war. And Fern? He's just another soldier now, a pawn with a name. He's no longer asking questions. He's not searching for his identity. He's doing what he's told, because if the world won't love him as Fern, it might at least fear him as the Green Knight. That's the most heartbreaking part of Fern's journey. Not when he dies, but when he stops trying to live. In Gumbaldia, Fern stands silently at Gumbald's side. Gone are the moments of introspection, the attempts to connect, the flickers of humanity. His movements are robotic. His speech is clipped. He's been given a role as a villain, and now he wears it like armor. But it doesn't fit. It never did, because Fern was never evil. He was just trying to matter. And now he matters to people who don't care if he lives or dies. He's been molded into a symbol of rebellion. Not his own rebellion, but someone else's cause, someone else's war. And the vines that once clung to his body, twisting, blooming, reaching for light, have become a cage. Fern no longer grows. He just obeys. But deep down, something in him is still waiting. Not for revenge, not for redemption, but for someone to remind him he's still human. And in the final act of his story, someone does. By the time we reach the series finale, Come Along With Me, Fern is a ghost of who he was, both literally and metaphorically. He enters the final battle as the same weapon, but leaves it as something far more human. When war between Princess Bubblegum and Gumbald seems inevitable, Finn and Jake decide to stop it the only way they know how, with magic, specifically nightmare juice, a psychedelic solution that plunges them Fern, Gumbald, and PB into a shared hallucination. Not a dream exactly, more like a mirror. And it's here, while untethered from his body, from his orders, from his past, that Fern finally begins to crack open. In the hallucination, Fern transforms into a monstrous bat-like creature and flies away in rage and confusion. But Finn doesn't let him go. He follows him, not with anger, but with understanding, because Finn now sees what we've known all along. Fern isn't just his rival, he's his reflection, a version of himself that was never allowed to heal. When Finn catches up to him, he doesn't fight. He speaks.
We're two sides of the same coin.
You'll never understand what it's like to be me. I'm tormented!
And Finn listens, if Finn can prove it. The two descend into Finn's vault, a metaphorical space that stores Finn's deepest, most private memories.
See? This is our shared torment!
Fern sees their similarities, and there, waiting in the shadows, is the root of it all. The grass demon. The thing that corrupted Fern's body, that twisted his instincts, that fed off his fear and isolation. And together, Fern and Finn destroy it. But there's a catch. The grass demon was what held Fern together. Without it, his body begins to crumble. Back in the waking world, the war is over, but Fern is dying.
Hey, Finn. I'm not doing so good.
Not in a blaze of glory, not as a villain defeated, but quietly, gently, like a leaf finally letting go of its branch. He tells Finn that he wants to go to the treehouse one final time, but when Fern is unable to make it, he has one final question.
Just promise to plant me there.
A simple request, a final act of belonging. The tree fort was destroyed in the battle. There's nothing left. So Finn does the only thing he can. He buries Fern where the roots used to be. And then something beautiful happens. From Fern's remains, a small green sprout emerges. Not just any sprout, but a seedling in the shape of the Finn sword. It's Fern, reborn. Not as a copy, not as a villain, but as something entirely his own. A tree, a legacy, a sword for someone else to wield someday. Fern was never seen in together again, meaning he's still alive as that tree many years later. He's finally his own to grow into the giant, majestic tree he was always meant to be.
Look at me. Okay? Like, maybe you guys will stop.
There are stories in gaming that feel bigger than the games themselves. Not because of win streaks, not because of subscriber counts, but because they touch something real, something human. Byron Reckful Bernstein was more than a streamer. He was a prodigy, a pioneer, and ultimately, a person overwhelmed by a world that never slowed down. His life was public, his struggles were broadcast, and his legacy is still echoing across the streaming world. Before he became Reckful, Byron was just a quiet kid growing up in Los Angeles. Born in 1989 to Israeli parents, Hebrew was his first language. He had two older brothers, Guy and Gary, and a natural inclination for games, music, and math. But Byron's childhood was marked by an unimaginable loss. When Byron was only 6 years old, his oldest brother, Guy, died by suicide. The trauma didn't just affect him, it defined him. It wasn't something he talked about in detail, but it colored everything. His relationships, his mental health, his need for connection. Fans who followed him closely could see the weight behind his eyes. Behind every joke was something he wasn't saying out loud. Byron found an escape and a new world in World of Warcraft.
Watch out! Okay.
Nice.
He stopped.
Right here, boys.
Dispel.
I can't play!
Like so many in the mid-2000s, he fell into Azeroth headfirst. But unlike most, he didn't just play the game, he mastered it. He gravitated toward the rogue class, fast, technical, lethal,
It was a perfect fit. Reckful's gameplay wasn't methodical, it was instinctive. While others played safe and calculated, he dove in with an elegance that felt more like improvisation than strategy. Between 2009 and 2011, Reckful dominated the WoW arena scene, hitting rank 1 multiple seasons in a row, 6 to be exact. He became a legend within the PvP community. The name Reckful was synonymous with rogue mastery, but it wasn't just his skill that drew attention, it was how he presented it. In 2011, Reckful released Reckful 3, a YouTube montage of his arena gameplay. It wasn't just another PvP video, it was cinematic, poetic. The music, the editing, the way the camera moved through battlegrounds and arenas. It felt like you were watching something important.
Stop him as he steps to Mayo, right there. Boom. Okay, I'm about to die here. I'm gonna blind this rogue now. I'm gonna jump before this. As this waylay fades, I got a big jump off. Now I'm just walking away. I'm waiting on cloaking. I'm not cloaking yet. He's gonna start casting on me.
Reckful 3 exploded. It became one of the most watched WoW videos of all time, and it put Byron on the map far beyond the boundaries of the game. He wasn't just a player anymore. He was a creator. Around this time, live streaming began taking off. Justin.tv had rebranded into Twitch, and Reckful, now already a known name in the WoW community, was a natural fit. But what set him apart on Twitch wasn't his gameplay, it was everything else. Byron didn't put on a show, he didn't act, he didn't brand himself, he just existed. He streamed his thoughts, his meals, his music. He'd go live and just talk to viewers. Sometimes he played games, sometimes he didn't. There were long silences, awkward pauses, bursts of laughter, moments of sadness. It felt less like a performance and more like watching someone live their life in real time. That honesty, that raw, unfiltered openness was what drew people in. He wasn't trying to be a celebrity. He was trying to feel less alone. But that honesty came with a price. As Reckful opened up more on stream, it became clear that he was struggling. He talked about depression. He mentioned bipolar disorder. He discussed feelings of inadequacy, isolation, self-hatred. Not in dramatic outbursts, just woven into his everyday conversations. And it was hard to tell where the stream ended and the cry for help began. 1 minute, he'd be joking with chat. The next, staring into the camera and saying, "I don't know how to be happy." This wasn't a character arc. It was his life. And thousands of people were watching. He didn't hide the ugly parts. He showed you when he was manic. He showed you when he was numb. And because of that, fans connected with him deeply. Maybe too deeply. Reckful became a mirror for a generation that was also anxious, depressed, and terminally online. But the difference was, he was doing it in front of the world. This was just the beginning of a story that would inspire, confuse, and devastate millions. The rise of a streaming icon, and the unraveling of a human being who changed the internet just by being himself. By 2015, Reckful was a fixture on Twitch, but his content was unlike anyone else's. While most streamers polished their branding and focused on gaming, Byron did the opposite. His streams were erratic, personal, experimental. One day he'd be playing Hearthstone or WoW Classic. The next he'd be interviewing a viewer about their anxiety or eating peanut butter on stream in total silence. And the viewers loved it. They didn't come for gameplay. They came for him. Byron wasn't a personality. He was a person. The charm came from his unpredictability, his sincerity, and his willingness to say exactly what was on his mind, even if it wasn't flattering, even if it was alarming. But as his channel grew, so did the emotional weight of carrying it. Byron often said that streaming helped him cope, that it gave him structure, connection, a sense of purpose. But that connection also had a darker side. Twitch chat can be supportive, but it can also be cruel. Reckful was often subjected to harsh comments, inappropriate jokes, and gaslighting, all masked as banter. His openness about mental illness made him a target. The internet has never been kind to vulnerability. Still, he kept going. Because for all the toxicity, there were also thousands who loved him, who needed him. He wasn't just their favorite streamer. He was someone who made them feel less alone.
I want to buy everybody's groceries. Can I buy everybody's groceries? on this card? No, I'm serious.
My friend is doing a game show, and you guys all won free groceries. All of you won free groceries.
Yeah. As long as they don't turn down my card because it's a lot of transactions. Let's try it out.
Yes.
Yeah, let's do it.
That pressure to entertain, to stay consistent, to survive, was immense, and he wasn't always coping. During this time, Reckful became closely associated with a group of streamers who, like him, weren't afraid to share their emotions on camera. Chief among them was Mitch Jones, another WoW player turned variety streamer who shared many of Byron's highs and lows. Their friendship was magnetic and messy. On stream, they were hilarious, riffing off each other, telling stories, making each other laugh. Off stream, they confided in one another about depression, drugs, loneliness, and fear. It felt like watching two brothers trying to pull each other out of a pit without a rope between them. But there were also falling outs, breakdowns, periods of silence, and then reconciliation. Other streamers entered the picture too. Trainwrecks, TV, Soda Poppin', Pokelols, Asmongold. Each had a different relationship with Byron. Some tried to support him. Others kept their distance. Everyone saw the signs, but few knew what to do. Because how do you help someone who lives their life on camera, but might be falling apart off it? In 2018, Reckful announced the most ambitious project of his life. He was building a video game. Not a shooter, not an MMO raid fest, but a social game. One that prioritized mental health, connection, and open dialogue. He called it Everland. The idea was beautiful, a virtual world where players could meet, talk, and grow emotionally, where strangers could become friends, and people with no support in real life could find purpose online. Byron poured his soul into it. He hired a team. He streamed development updates. He shared ideas and philosophy in public chats. Everland became more than a project. It became a mission. But it was also chaotic. Byron wasn't a trained game developer. He had vision, but struggled with leadership. There were internal conflicts, missed milestones, funding problems. Members of the team came and went. Public updates slowed. Hype faded. It started to feel like the game wasn't just for the players. It was for Byron, a world where he could finally feel okay. But the more he struggled with Everland, the clearer it became. No digital space could fix what was breaking inside him. In 2019 and early 2020, there were flickers of hope. Byron talked about going to therapy. He spoke more openly than ever before about his bipolar disorder. He shared the things that were helping: medication, routine, real-life conversations. He smiled more on stream. He released a video series where he interviewed strangers about meaning and connection. It was thoughtful, unpolished, and entirely him. There were moments, days, even weeks, when it seemed like Reckful was healing. But mental illness doesn't follow story arcs. It loops, it crashes, it surprises you. And behind the smiles were moments of detachment, long pauses, tweets that hinted at darkness, streams that trailed off without endings. Some friends reached out. Some didn't know how. His community saw it all. But as always, it was impossible to tell what was real and what was just another part of his openness. In early 2020, something seemed to shift in Byron. He was streaming less frequently, but when he did, it felt lighter. His tone was softer. He talked about working on himself, eating better, sleeping more. He even posted a spontaneous marriage proposal to a woman he'd been seeing, a moment that was awkward, heartfelt, and deeply Reckful. He was taking walks, meditating, talking more about his plans for Everland. For a brief moment, fans let themselves believe, maybe this is his arc. Maybe he's turning the corner. But there were still signs, the occasional monologue about not fitting in, questions about whether happiness was even real. Viewers would watch him smile one day, then tweet about worthlessness the next. The gap between hope and despair was narrowing, and it all came to a head in July. On the morning of July 2nd, Reckful posted a series of cryptic tweets. Some were romantic, others were scattered. One simply said, "Please just know in these situations, the insane person does not feel in control of their actions." Another read, I feel bad for anyone who has to deal with me when I'm crazy. Then, nothing. Byron Bernstein died by suicide that same day. He was 31 years old. News spread across the internet within hours. At first, fans didn't believe it. Then confirmation started flooding in, from friends, fellow streamers, and eventually his family. The shock was overwhelming. Twitter became a digital memorial. Reddit turned into a space of mourning. Twitch was flooded with tribute streams. People who had never watched Wreckful before were suddenly learning who he was and what he meant to so many. What followed was unlike anything the gaming world had seen before. Streamers stopped midstream and broke down crying. Clips of Wreckful began circulating, him laughing, dancing, being vulnerable, giving advice. Entire guilds in World of Warcraft gathered at his in-game memorial spot. Blizzard, the developer of WoW, added an official NPC in Stormwind named Wreckful, who trains rogues, a permanent tribute to one of the greatest players the game had ever seen. But the mourning wasn't just about Byron. It was about what he represented. He had become a symbol of a generation raised online, struggling silently, hoping someone would listen. His death wasn't just a loss. It was a mirror. Twitch wasn't ready for someone like Wreckful. Few people were. He exposed how unequipped the streaming world was to deal with mental illness, how parasocial relationships blur the lines between empathy and entertainment, how streamers are often rewarded for oversharing, but punished when the truth becomes too much. Byron lived with no filter, and while that gave him power, it also made him fragile. Because when you lay your soul bare to the internet, you give the world permission to judge, exploit, and misunderstand you. In the wake of his death, the community had no choice but to talk. Big streamers began speaking openly about their own depression, burnout, and therapy experiences. Viewers became more careful with their words. Twitch even started promoting mental health resources and partnering with wellness nonprofits. But the truth is, the damage was already done, and Wreckful had paid the price for being too ahead of his time. To his fans, Wreckful was more than content. He was comfort. A friend you never met, but felt like you knew. Someone who made it okay to be weird, to be unsure, to be unwell. For many, he was the first person they ever heard talk about depression, about grief, about losing a brother, about waking up and not wanting to be awake, about how love was terrifying and beautiful at the same time. He didn't teach these lessons like a therapist, he lived them in front of thousands. And we watched, powerless, grateful, changed. After Byron's death, the gaming world didn't just grieve, it changed. His story became required watching for any streamer who thought honesty was just a content strategy. He was no longer just a rogue god or a Twitch pioneer. He became a symbol of what's possible, of what's vulnerable, of what's at risk when the lines between life and live stream disappear. But if you asked him, he never wanted to be a symbol. He didn't want to be a cautionary tale or a martyr. He just wanted to feel okay. He wanted others to feel okay. He wanted to build something that helped people connect so they wouldn't have to feel what he felt growing up. And in some ways, he did. He helped shape the way creators talk about mental health. He broke the mold of what a streamer could be. He made it okay to cry on camera, to pause a stream and say, "I need help." Even Everland, though unfinished, lives on, not as code, but as an idea, a place where people are honest, where strangers talk like old friends, where you can walk through pain, not hide it. Byron Bernstein didn't teach through lectures or tutorials. He taught by example, and sometimes by mistake. He showed us the power of openness and the danger of it. He showed us how streaming can build community and how it can isolate you further. He showed us that being real can be the most magnetic thing in the world, and also the most painful. But more than anything, he showed us that behind every username is a person, a whole, complicated, hurting, beautiful person. And maybe that's the most important thing he left behind, a reminder that empathy is not optional, that what we say in chat matters, that how we treat the people behind the screen can change everything. He didn't save the world, he didn't save himself. But for a little while, Wreckful made the world feel smaller, softer, safer, and maybe That's enough. Today, if you visit Stormwind in World of Warcraft, you can still find him, the NPC named Reckful. He stands quietly, a rogue trainer in the place he once dominated. Players kneel in front of him. They type / cry, thank, dance, not because they need training, but because they remember, and they're still not ready to let go. To Byron, thank you for everything.
I feel like people are always too scared to meet new people, try to meet others. Anyway. Goodbye, everybody. Like, yeah, I mean each other, yeah, in chat. Because you probably have, there are probably a lot of like-minded people in the chat at this moment, you know? Have a good night. See you guys tomorrow or the next day.
Want to make heat engines, we want to take like this resource, heat, like I burned some wood, I have some hot gas, and I want to turn this into movement. So there was this idea of like heat is like energy, but energy that I don't control, and work is like a train moving, like energy that I can actually control.
Yeah, check.
Now, given our initial conversation, we can already see that these are subjective kind of concepts, and so here's an example of this. So then with time, like, although it started with these very kind of practical purposes, then it became more of a theory about, yeah, the world, how, you know, what thermodynamic processes go on in our cells or in some natural thing we observe, or when we put two materials together, what's the heat flow like? It looks like a very objective thing from the outside.
Yeah.
And then Maxwell came up with this thought experiment, okay?
Yeah.
So let's start with the gas. What is a gas at a certain temperature? It just means like, from the beginning, people already knew like the gas was made of particles, right? And they're moving at kind of random speeds and directions.
Yeah.
So I'll write here like a small arrow if the particle is moving slowly, and a fast arrow if it's moving thing. But we don't see this, right? So all we know is some macroscopic properties of this gas, like the temperature, the pressure, the volume, right? Which all result from these microscopic quantities that we don't have access to.
Yeah, and they smell it equally in the room if it's a gas that I can smell, right? It's not just local that I only smell it.
Yes, no, it's kind of spread out here in this whole box with gas, right? And one of the laws of thermodynamics, like one of the formulations of the second law is like you cannot just take heat into work. You cannot take energy that you don't control into energy that you control. Normally you need like a cold gas and a hot gas. And now from this difference in things, then you can build a fridge or you can build whatever, right? Okay, and then Maxwell thought, okay, yes, sure, we cannot see the position and velocity of all these particles, but now imagine that there's no reason why someone couldn't. So imagine now we have like this demon. He has like microscopic vision. He can actually see all these particles. And this demon puts like a little partition here in the middle of the box and has a little gate. Okay?
Yeah.
And now this demon can kind of control when to open the gate or not. And he opens the gate if there's a fast particle coming this way or a slow particle going the other way.
Yeah.
Yeah, so after a while, what do we have?
He's separating the two gases.
We have all the fast particles here, lots of kinetic energy, and all the slow particles there.
Yeah.
Okay, so this means that this is, in practice, this is a hot gas, because on average, the particles are faster, and here this is a cold gas.
Yeah.
So from a single temperature, now we created like two temperatures. Okay, so what does the demon do now? Well, it can, for example, try to extract work from here. So put some system of pulleys here, some buckets, and a hot gas will try to expand precisely because these are these particles with more energy can expand against this cold gas. So this thing moves, and this goes up, and now we have we lifted a bucket. This is the same way that dams work for production of energy, right?
Yeah.
You pump this thing up here in the Netherlands, so
we do a lot of pumping.
Lots of pumping up, which usually costs work. Like, look, I did it for free, right? Yeah. So I created work, energy that I can control from heat.
Yeah, the only sort of what I would say is that opening and closing the door would take some energy also for him to do, or?
In principle, not. I mean, not to the same.
Yeah. Okay. Check. So that it's very much about sort of he just doing like with minimal work, separating those two. Yeah. And then you can extract sort of work from the system, which sort of basically gave you free energy.
Looks like he gave me free energy, right? And now at the end, so I have like, okay, now at the end, after this expanded as much as it will expand, I just remove the partition, I put it back in the middle, let the particles mix again, and then I go back here.
Yeah, and then
I do it again. Yeah. Perpetual motion, right?
Yeah,
so violated the second law of thermodynamics. Yeah?
Yeah.
So what's the...
Yeah, and in sort of entropy talk, sort of the initial state is high entropy, and the daemon is able to bring it back to low entropy and go back to high entropy. And
this already tells us that there's some issue with the notion of entropy, right? Because one way to look at it is to say, for us, the state has high entropy. But for the daemon, the daemon has perfect knowledge of everything that's going on here, right? For the daemon, it has low entropy. But if you just want to look at it from the outside and say, okay, why is this not a reverse, like not a reversible, but a perpetual motion engine? Why can I not repeat this forever? The solution is kind of bringing the daemon inside the theory. So instead of just applying thermodynamics here, I move kind of the Heisenberg cut of my theory. So I say, no, the theory should treat also this daemon as a thermodynamic system. So what's going on in the daemon? So he has to store this information somewhere in the brain or memory or computer of which particles are fast and slow.
Yeah.
Right? So this is like a hard drive that the daemon is filling in.
Yeah.
Right? If he repeats this a few times, then he'll have to erase this hard drive or buy a new hard drive. Then the hard drive is a resource, right? And then what Charles Bennett and Rolf van Douwer showed is that actually how much it costs you to format this hard drive again is precisely the work that you gained here.
And that we know mathematically, that's just physics.
Yes, this is the physics. So these two things cancel out.
Yeah.
So this is an example of like, oh yeah, even in classical physics, sometimes we need to bring the observer inside the theory, otherwise our analysis just breaks the theory, right? The theory does not apply it just at this scale, and you need to really consider it.
Yeah, that's really interesting when I saw sort of that erasing information costs energy, and it's the same energy that is gained in sort of this free energy example.
Yeah. So another way to look at it, if you don't want to model the memory explicitly, is like, no, this is a set of low entropy for the daemon.
Yeah.
He's just transforming like the information he knew. Like he had information and energy here to information and energy here. Yeah. And then at the end he lost information about where all these particles are. Now again, if he wants to repeat, then he needs to gain this information again, and this again costs work, right?
And if we now sort of make this sort of, I like this analogy, I think it's very good, it's very understandable. If we now make it quantum, what would sort of be the sort of the quantum version of Maxwell's daemon?
I mean, one can do the quantum version of Maxwell's daemon. And then there's funny things like a quantum daemon can actually extract even more work than a classical daemon, because you can have quantum knowledge of like, if his memory is entangled with these particles, not just classical correlations, then you can even extract more work.
Okay.
But maybe we can talk again about a quantum measurement and a quantum
an analogy.
observer.
Yeah, that's better, I think. Yeah, cool.
Yeah. Okay, so now let's talk about quantum measurements a little bit.
Yeah.
And now let's think again. So I have Alice here, and she's trying to measure, I don't know, the spin of an electron.
Yeah.
Okay. And this thing is in a superposition of being up and down with different weights, which translate to different probabilities of seeing one outcome or the other.
Yeah.
Okay. So then let's say now she's inside her lab. So this is Alice. She's measuring some system. Oh, and now from outside there's someone else. And normally I draw the outside observers with hats. Okay, so this is Ursula. Wigner will show up later because we're building up to a bigger experiment, right? So what is happening here? So from the perspective of Alice, she's making a measurement, getting a single outcome.
Yeah.
From the perspective of Ursula, Alice is just getting entangled with this thing.
Yeah.
Okay?
Yeah.
There's no single measurement from her perspective. She knows that Alice is a single measurement, but the whole state is a superposition.
Yeah, it could really be both spin up, spin down. Yeah.
So I'll write this as a little circuit. Okay, so we start with like, this is the thing she's measuring, your thing. Here's Alice, okay? And time goes left to right. And now there's some operation here. So in quantum mechanics, this is a control NOT gate. It doesn't matter. It's something that in principle, Ursula can come here and reverse. Yeah, shoot some lasers at it, reverse the operation. Okay, and then we'd go back to the initial stage.
Okay.
So Alice is kind of braiding herself with R. So far, this is what's happening from her perspective. From Alice's perspective, what's happening is something different. So if I use squares for reversible operations, then I can use, I'll just write it here, then I'll erase. Then I can use like this for measurements.
They're irreversible.
For irreversible measurements. This is like the traditional symbol. Or even like something like this that has a pointer that shows us what's going on, right? So from Alice, this is happening. She's measuring R. It's a irreversible thing. She gets a single outcome. From Ursula's perspective, no, there's a reversible operation going on. Okay, so now, so far so good.
Yeah.
I can make it a little bit more complicated.
Yeah, so Ursula can, when we say it's reversible for Ursula, it, because Ursula hasn't yet sort of performed a measurement on Alice. She hasn't performed anything, right? So
so it could be, it could mean two things, right? So one thing it means is that Alice puts the Heisenberg cut just around this particle.
Yeah.
Like in the Maxwell's lemma, we're just looking at the box.
Yeah.
Whereas Ursula is putting her Heisenberg cut outside the whole thing.
Yeah.
Okay?
Yeah.
And for now, it's just a matter of perspective. I'm looking at it from two different points of view. Later on, yes, Ursula will come here and do some other joint operation that undoes what Alice did.
Yeah.
Is that okay?
Yeah, that's okay.
Yeah, okay. So now we forgot about Ursula for a while, and let's talk a little bit about reasoning, logical reasoning. Very simple. Okay, so we had another thing. We say that Alice, so she's measuring the spin and can get two outcomes. Let's call it 0 and 1. Is that okay?
Yeah.
And Alice says, okay, she has a second spin here that she'll prepare. Yeah, and Alice says, okay, so if I get my outcome to be 0, she gets an outcome, she prepares the second spin in some state up.
Yeah.
If she gets the other outcome, she'll prepare the state in what we call a superposition of being up and down.
Check. Yeah.
Okay, something you can do in the lab.
Yeah.
Nothing special about this.
Depending on her measurements, she prepares another particle in a either defined spin up or superposition spin down up at the same time. Yeah.
Okay.
Yeah. Check.
Right. She sends the second spin to Bob. Who's Bob? So Bob is here inside his own lab. So now he got the second spin. Okay.
Yeah.
It's in some unknown state for him. Alice knows what it is. Bob doesn't know. Bob measures it. Again, up or down. Two outcomes can be 0 or 1.
Yeah.
Okay? So if he measures this,
it could be still both, right? Because the other one.
If it's this one, it can only be 0. Because it's 0 is up, say.
Oh yeah.
Okay. So if you do this, then B is 1 for sure. But this is a superposition of up and down. Okay. So if he does this, then B equals 0 or B equals 1, 50-50 probabilities. Yeah, from my perspective. Yes.
So yeah. I thought because if A is 1 for Alice, she prepares the sort of superposition. So it could be both up or down.
Yeah.
So the only way to know for sure, the only certain information you can get from Alice's lab is if you measure a down, I'd say, right? Because that's the if Bob sees a spin down, then he knows for sure it must have been the superposed.
Should be 0. Sorry.
Yeah, check.
This should be 0. Yeah, this should be 0.
Yeah. Then,
0 means up. And
yeah.
Okay. Yes, exactly. So there you go. So now the game is exactly what you said. So the game is now Bob. Bob doesn't know what Alice measured, what she saw. He just did this measurement, and now he needs to guess what Alice did.
Yeah.
Okay. So if you obtain 0, sorry about that before. So if you obtain 0, he doesn't know, right? It could be in this case, or it could be in that case.
Yeah, could be both.
Could be both.
Yeah.
But if you got 1, then for sure he knows that.
Yeah.
You know, the only way for me to get 1, Alice must have prepared this thing. Therefore, Alice must have obtained.
Yeah, so if I got spin down, I know for sure it must have been 1 because that only the superimposed particle can give me spin down.
Yeah.
Yeah.
Okay, so this is the reasoning. So if B equals 1, then A equals 1. Okay.
Yeah.
For classical analogy, if this was not a spin and this was a coin, we can still do the experiment. So at this point, we can still do the experiment. So Alice flips a coin. If it's heads, she prepares a second coin in heads.
Mm-hmm.
If it's tails, she prepares a second coin by just flipping it, not looking at it.
Yeah.
Sends to Bob. Bob then looks at the coin. If it's heads, he doesn't know which one it was, but if it was tails, he knows that, okay, Alice must have done tails, right? It's the same thing, I just added a... replace the coin with a quantum measurement so far.
Yeah.
Which will only be important later.
Yeah.
But this is the kind of reasoning that we think is very natural.
Yeah, and Bob so knows 2 things. He gets a particle with something he can measure, and he has to know how Alice reasons, right? He knows exactly.
Yeah.
He knows that.
Yes, we know this. Yes, it's not a adversarial scenario. Everyone knows the recipe for what everyone is doing. And now we can think like in this scenario, what is Bob's Heisenberg cut? Well, he's reasoning about Alice's outcomes, so he believes that Alice saw an outcome.
Yeah.
So for him, Alice is classical. He's outside the Heisenberg cut.
Yeah.
But of course, these 2 particles are quantum particles. So like his Heisenberg cut includes these 2 things.
Yeah.
Yeah. Can I add one more agent? Because now it's where it gets a little bit more complicated.
Now it gets if we put agents outside the labs, right? Also watching at Alice and Bob.
Yeah. So I'm building up to the Fraudiger-Renner experiment, which is an extension of Wigner's friend that was proposed by...
Yeah, we have 2 Wigner boxes here, basically, right?
Yes, we have 2 Wigner boxes, yes.
Yeah.
So Ursula is friends with Alice, and Bob is friends with Wigner, who is outside here. Huh? Okay.
Yep.
So now, after Bob did his measurement, sometime later, Wigner will measure this whole thing. Okay, so let me now draw the rest of the circuit of what's happened here.
Yeah.
So, Alice, depending on what she saw, so depending on what's on her memory, she did some operation on this particle S, okay? This is again a logical gate, just with quantum particles.
Yeah.
And then Bob measured this particle S.
Sorry, S is the particle.
S is the second particle,
Oh yeah, that's the particle that Alice prepared and
that
sent.
Alice prepared
sorry,
to
yeah,
Bob.
I'm seeing. Yeah, S is sent. Yeah.
And then Bob measured S, which seen from the outside, if I'm look at like perspective from the outside, from us, it's also some kind of operation. It's also this control gate that can be reversed in principle. Yeah? Good. So this is what it is. This is the whole circuit. And now Wigner is going to come here and do a big measurement on both the lab and this, which in practice corresponds to something that undoes this measurement and then does some...
This is really funny. This is a new way for me for looking at it when you put it like this in this logic gate, or what's the way to say it? What you're doing here with putting it in these lines?
Yeah, I'm putting it like a quantum circuit. I'm designing it like a quantum circuit. Yeah, sometimes it's very helpful too.
Yeah, makes it sort of, at least so far, I think I still get it. Yeah.
So if we give names to these operations,
okay,
so let's call this It's an operation U, which is a C note. This I call it V. It's a controlled Hadamard. If you want to know this, again, U. And this is kind of U minus 1. It's the reverse of these two things. Meaning if I do this and I do that, this is the same as doing nothing.
Yeah, okay.
It's the identity. So it's like I go, you know, like you're watching a movie, you go skip forward, skip back, you end up in the initial state. Okay?
Yeah.
So Bob did this, Wigner does this, and then he does a measurement here. Okay? Which is a different measurement than what Alice and Bob were doing. Okay. But it's a measurement such that, and now is the part where, where if the initial state of this particle had been this, okay, where if we had like A equals 1, then Alice prepared S in this superposition, which then got kind of entangled with Bob's memory. And I'm trying really hard not to draw any formulas, so let's just say like they're entangled, like a braid. Yeah. And then Wigner does this thing. And what the math tells us is that if he does this measurement, then he'll always get some outcome, which for the purpose of this experiment, they call this outcome, they labeled it fail.
How?
Fail. Like,
fail, yeah.
Like succeed or fail.
Yeah.
And the measurement outcome is fail. Okay, but we could call it 0 or 1, but fail is more. Okay? So this is kind of the, without formulas, what would happen? It's just like this entangled stage that is happening here, that we have here at this point.
Yeah.
If Wigner does all this, and we had started off with the S that Alice prepares if we had 1,
and
then he always gets the same outcome.
Yeah.
Okay.
Always get that outcome. Okay,
always
for
gets
me,
that
I
outcome.
guess okay, if all of this happened, he will always get that
He
outcome.
will always get
if
this
Alice
outcome.
prepared sort of.
If Alice prepared this from Alice's perspective, right? So which means that now Alice, what is Alice's Eisenberg cut? So now she's treating, I mean, all of this as a quantum system, and R, of course, because he needs to think, Bob thinks he's making a measurement, but he's just really getting entangled with S. I don't need to think about Bob's outcome, just that they are like in this joint state, this entangled state that if Wigner measures, he'll always get this outcome. Yeah. Fail, okay?
Yeah.
So then Alice's chain of reasoning is, okay, then if I start with, when I measured this first particle, I got 1.
Yeah.
I prepare this state,
Wigner must get
Wigner must get fail.
Yeah, that's okay. That's the logic of the experiment. Yeah.
Okay, so then we have A equals 1, Wigner equals fail from Alice's perspective. Yeah. What does Bob think? Now we go back to Bob's thinking. Just after he got S, if he tried to guess what's the outcome of
for Wigner.
For Wigner, yeah. He thinks, well, if I got 1, we'd seen before, then I know that Alice will get 1. And I know that Alice knows that when she gets 1, Wigner will get fail.
It just feels like a circle, like sort of,
Well, at this point, it's not a circle yet. It's kind of a chain of like, I got this. Starting to look like this meme. Okay.
Yeah.
Starting to look like this meme. Okay.
Are they communicating here, or is this just
they
them
don't need
reasoning?
To communicate, right? It's just reasoning, right?
Them reasoning about sort of what other agents will see.
Yeah, it's just reasoning about what our agents will see. And the part that you need to take my word for it is that, in this step, Wigner will always get fail if he sees this because that's quantum mechanics. Yeah. And the part that's also strange is that, Bob sees himself as classical, but for all this reasoning, he's taking into consideration how Alice thinks, and Alice sees him as a quantum system, right?
Sorry, again, how's that sort of the what?
We're doing this chain of reasoning across kind of different cuts of the different Eisenberg cuts for different agents. But this still goes perfectly so far, okay?
Yeah. It's no paradox at this
There's
moment.
no paradox at this point. It's an experiment you can make with, a small quantum computer with quantum bits instead of observers, and you just run the circuit and you do a measurement here to see what did Alice get, what did Wigner get, and they're always, this is true.
Yeah.
Good. The problem is that if I put another agent here, Ursula, and she does some measurement in Alice, then this whole thing will break down.
Okay.
Because, let me try first without going to the maths.
Yeah.
What they found out is that,
It's just funny because this is like a very long, complicated way of saying that stuff is still just very logical. If you apply the logic, you get the same results.
You just apply the logic,
We just made it very complicated with this quantum setup. But okay.
Yeah.
But we need that. We need that because we want to understand why things break down if we add another observer. Okay, check.
So what will happen is that here, at some point, maybe before Wigner's measurement, Ursula will do the same. She will kind of undo Alice's measurement. She'll perform a big complicated measurement here, right? She'll get some outcome, which can be again okay or fail. Okay. And and then she'll reason the same way that if she gets by just looking at the whole quantum state, she can see that if I got okay, then Bob got 1.
Okay.
I'm not explaining you this, but it's something similar to this.
Yeah.
Right, so she sees Alice as being in this superposition. She knows all the things that happen until here. She thinks of Bob as like outside the cut because she wants to reason about his outcome. And just from the properties of the quantum state, she deduces that, okay, if I got this outcome, Bob got 1. Okay?
Yeah.
So now if we chain the whole thing.
Yeah, because measuring Alice in his lab gives Ursula information about what Alice sent to Bob. So then she knows what Bob sort of got. Yeah.
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 In a way.
Yeah.
Yes. Yeah. So if we chain the whole thing, what Ursula knows is that if she got okay, Bob got 1. She knows that Bob knows that if he got okay, that if he got 1, Alice got 1.
Yeah.
And she knows that Alice knows that if she got 1, Wigner got fail. So far, so good. It just looks like, okay, if Ursula gets okay, then
Wigner gets fail.
Wigner gets fail.
Yeah.
Now the problem is that if you just look at, now we look at it from the outside, we just look at this whole quantum circuit here. So we put our Eisenberg cut around the 2 labs. And just think, all these operations happen, and at the end we do these 2 measurements.
Yeah.
There is a probability that they're both okay.
Oh, but whereas we just said when one measures okay, the other one is fail.
Yeah. So yes, that's that.
And you say 1/12 of the time.
Yes, this is something you can deduce from the maths. You just look at this whole quantum state, you run this circuit, and then you do these measurements.
Crazy.
1/12 of the time.
Okay.
They'll both get okay.
Yeah.
The problem is now when they both get okay, Wigner asks Ursula, so what did you get? And she's like, oh, I got okay. And Wigner goes, okay, so I know that you got okay. So Bob got 1, so Alice got 1, so I must have gotten fail. But look at my measurement outcome. I got okay.
So and then he would say, you have to have seen fail. You have to have a fail because I have okay.
Right, but he's like, no, look here it is. I got okay.
And there's and none of them can then sort of say there's an error. They know. If we compare it to just nodes in a computer network, they know the system, the transistors, everything is just the algorithm is okay, the system is okay. It's just a paradox.
Right, at this point it'd be just a paradox, right? Everyone used very reasonable logic. So what is breaking down? So some things...
What's breaking down here?
Yeah.
Logic, I'd say. Logic is breaking down.
So
And also with accuracy, 1/12 of the times it will happen. That's sort of the mathematics tells you.
Mathematics, that's 1/12 of the time they'll get this result. Both get okay. And whenever this happens, then always they'll find the contradiction.
And you cannot sort of say when. So it's almost as if you have sort of, you know that you have an error. You can accurately say I have an error 1/12 of the times. Let's call it an error.
Yeah.
But you cannot predict when you get the error.
Correct. Yes. I mean, yes. Yeah. That's right. Yes. So.
Yeah. So and when you get an error, you don't know who's wrong or right. I mean.
Right. This is a decision.
There's no. Or can we stand outside and say Ursula's right or Wigner's right? Or
you can say what you want, but this is still your choice, right? Something made you decide which one of them is right. Like maybe some philosophical principle that you have. Maybe you think, look, no, it's much more immediate that Wigner looks at here and says, okay, so this must be the right thing. Yeah. Whereas going through this chain of reasoning, something must be wrong with that.
Yeah.
Right? But again, this is a decision you make.
Yeah, and just for ours, we will share like the whole experiment and the papers and stuff. So we have the explanation here. We will share it.
Yeah.
I can hardly follow. I do follow because I've read the paper, but I'm of course, as I said earlier, I'm very much in it for the philosophy. So I'm just like puzzled here because we have a logic breakdown, a very quite profound paradox here. I always find it hard because I'm just not in that sense analytic enough. I know that how you present it is correct. So, and I follow sort of the steps. I just find it hard to keep it all together in my head.
Right. So maybe what I can tell is like each of these inferences, we saw how to do it. Like we saw this one we followed very well. Bob trying to guess Alice's outcome could be done classically. Yeah. It's a very logical little thing. Like this one and this one are a bit more complex and I cannot explain it without math. I just have to tell you like, yeah, look, Alice looks at the quantum state that she prepares, knows how it evolves when Bob entangles, and then knows that from here, Wigner will always get the same outcome, fail. Mm-hmm. So the same kind of reasoning is just a little bit more involved to explain without maths. And this is the same, right? So all the individual steps, this is just like applying basic logic and a little bit of quantum mechanics.
Yeah.
The problem comes when we start to combine them. Yeah? And now, what are some ways out of this paradox, okay?
Yeah.
So one is like the many worlds view. It's like, okay, maybe this is just an expression of many worlds view where like, yes, Wigner sees one outcome, but he also sees the other outcome. Okay, so it's like saying, okay, maybe in your logic system, you know, logicians can come up with whatever logic systems. It's just maths, right? You just put some axioms in and the machinery gives you some things. And one of the axioms you can put is saying like, no, it's okay for Wigner to know that he gets an outcome and also that he gets the opposite outcome.
Yeah, to basically say I'm okay with facts that seem to be in contradiction, but I can account for that because I say it's many worlds interpretations. We're on a different branch of the wave function right now or something like that.
Something
right?
like that, yes. The problem is then, okay, and now you try to apply that kind of logic as you go through the world and try to make decisions. And it's not a very useful tool, right? Because it's a logic where like, yeah, I can get hit by a car or I cannot get hit by a car. So I'll just cross the road. I don't know.
Yeah, it's not very operational.
It's not very operational, right?
No. Okay, so many worlds would say that's what's happening here, and then that's why it seems like a paradox. Yeah. Okay. So
there's many worlds. Yeah. There's more many worlds, and there are many world believers. Yeah. So some people who believe in many worlds, and on some days might say that. So another way out of this is just saying no. We're trying to combine all these statements.
Yeah.
But we're combining them kind of across different physical theories in practice. Okay, it's like is it as if I was trying to combine, I don't know, we're analyzing some political situation, and there's a chain of people that need to give us insights, but each of them has such different approaches that at the end, like you get just a like, I don't know, the things are incompatible.
Yeah, because they're applying different forms of reason or logic.
Yes,
or even...
so it's not the logic they're applying that's different, but they're modeling the world differently. So Alice is modeling this and this as quantum systems, whereas Ursula is modeling all of Alice's lab, including Alice's memory, as a quantum system, right? And Bob is just modeling the two particles as quantum systems. So we're having agents with different Heisenberg cuts.
Yeah.
And clearly something goes wrong when we try to combine logic across these different Heisenberg cuts.
Yeah, and what interpretation of quantum mechanics says, yeah, we can expect these paradoxes to arise then if you model differently? Is that...
I mean, most of this kind of objective versions of Copenhagen interpretation. So neo-Copenhagen interpretations say the Heisenberg cut is a tool that we use to separate what we treat as quantum from what we treat as classical, but where you put this cut exactly, you know, whether you include the protons inside or the photons that hit your eyes, like, it's kind of flexible. And agents can put it at different points. Right, so this would be one option. And then maybe a more objective Copenhagen thing would be like, no, there's limits on where we can put this thing. Maybe like, if you're in some kind of multi-agent system and there's people who consider each other agents, then no Heisenberg cut should include other agents as quantum systems, right? Otherwise the logic breaks down. Something like this. There's also, of course, collapse theories, which just tell you, no, you cannot put the Heisenberg cut around Alice because there's some objective collapse going here. The systems are too large. There's too much dissipation with some environment or some background field, whatever. And this is not this evolution. This gate is wrong.
Yeah.
Okay? And that's just saying, okay, quantum mechanics does not apply at this scale.
Yeah.
So most physicists at the moment, they think the way around this is by saying, no, there must be some compatibility conditions between Heisenberg cuts, some rules for when can I combine this reasoning, even if we model different systems as quantum or classical, and when can I not?
And if we know those rules, we won't get the paradox.
This would be the case. Then the solution would be like, in this case, this violates these rules, so you should not be allowed to change statements like this. Right? Okay, so now we have this extravagant thought experiment that will never be realized with people because this involves extremely complicated measurements, but which teaches something. It's teaching us that like the way we're using quantum mechanics is kind of breaking down at this level. Okay? Yeah. And an analogy to go back is like Maxwell's demon again. So Maxwell's demon is an experiment that again will not be made with a real demon and all the particles of a gas. And again, it shows, oh, look, thermodynamics is breaking down. So what solutions are there? And one solution was, okay, we need to bring the demon inside the theory. Another solution would be, no, we keep the demon abstract, but we take the perspective of the demon. And then from the perspective of the demon, it was work all along. We never had heat because they always had information, right? So now what can we do here? And this is related to kind of, this experiment can be formulated as a no-go theorem based on some assumptions, but the solutions are this. So one option is say, quantum mechanics does not apply at this scale. There's some objective collapse going on. This is not the right circuit.
Yeah, you cannot treat someone in a lab being in a superposition. There's
Option two is saying, well, maybe it's okay that you can get to different conclusions from different paths, because many worlds I do see okay and fail.
Yeah.
Another thing is like what cubism says, like quantum theory is a theory that helps me reason and make predictions. I always take my perspective to do this in a kind of a radical way, which means I should not be considering the points of view of other people at all.
Yeah.
At least this is what cubism would have said 5-10 years ago.
Yeah.
Although things are evolving also within that interpretation. And finally, the other way out is just saying, no, we just cannot change these statements because we're combining different Heisenberg cuts. And we need to find some kind of rules for compatibility between Heisenberg cuts. Okay? And the problem there is that whenever we find these rules, either they are so strict that, okay, we don't find a paradox here, like, okay, I can always think of your knowledge if you have exactly the same Heisenberg cut, but then there's many applications where this theory is useless, I can't make prediction. Or it's a bit more generous, like, okay, if our Heisenberg cuts don't exactly match, but they're a little bit, I can still think of you as an agent and do this reasoning. I know that you know X. And in those cases, in general, we can find a paradox. So we change the setting a little bit and we find a paradox. Right? So there's no kind of easy solution as of now.
They all come at a price, right?
They all come at a price, yes.
Yeah. And they all are so counterintuitive in how we experience the world.
Yes. It's the same idea as in Bell's theorem, right? You start with very intuitive assumptions.
Yeah.
And you find a contradiction, so you need to let go of one of them. And then none are good. Yeah,
so we have different observers, all reasoning quantum mechanically, and we are syncing them up, letting them communicate with each other.
Or let them thinking about each other's thoughts.
Yeah, but I mean, there's interactions. We have one preparing a particle, and then
the
goes in between, and then we end up with just different stories.
Yeah.
Different stories about what's really the case, or what is sort of
about what happened.
That's super weird, right? Yeah.
Yes, it's like they really experience different realities, right?
So we have thought experiments, physics that enter sort of the arena of metaphysics, that it doesn't tell us what sort of reality fundamentally is, but it does tell us that certain assumptions cannot be true at the same time, right? If you sort of apply that approach, so the no-go theorem approach, and the metaphysical assumptions that are put to the test to this particular thought experiment, the FR thought experiment, what are sort of the assumptions underneath this experiment that cannot all be true at the same time?
Right. So there's many ways to formulate the assumptions. It's like you formulate a set of assumptions, and the experiment is kind of the proof that they cannot all go together.
Yeah.
Right. So in the original paper by Daniela Frauchiger and Renato Renner, so they had, I think, 3 assumptions. One is that quantum mechanics applies at these scales. So I'm not even saying like universally, but that I can put you in a box and model you as a quantum system. Like the agents could model each other as quantum systems.
Yeah.
I'll just go through the assumptions first.
Yeah,
right?
then we can go and I'll ask questions per assumption. Yeah, good thing.
The other thing is something about logic, but it's also, the way it's phrased, it's like a mix of logic and something about quantum physics. It's like, I cannot conclude one thing and its opposite. If I'm Wigner, I cannot conclude that I'll see the outcome okay, and also that I will definitely not see this outcome okay.
Yeah, just not have that contradiction.
Not having this contradiction, right? It's something about logic. It's also something about our experience of a measurement.
Yeah, which sounds super commonsensical.
Yeah. The other thing is consistency of the theory across different agents. And this in practice, what it means is really that I know that Ursula knows, that Bob knows, that Alice knows X, and I can chain these statements.
Yeah.
Right? Which is, again, how we go through life and how we make decisions in most settings. So the thing the assumption that is kind of hidden here among all of this is like this freedom that agents have to decide where they put the Heisenberg cut, decide which systems they model as quantum and which model as classical, and that these other assumptions work together with this, right? I can do these chains of reasoning across agents that have different Heisenberg cuts, but that's about it.
Yeah, okay, check. That's an extra nuance on top of this, which we can go into.
Yeah.
But first, to check them off, right? So, are these assumptions to me sound very commonsensical also for physicists prior to this thought experiment? So, if I ask the question differently, was this sort of a bomb dropped in the foundations of physics, this thought experiment? It does seem to me like pretty new, right? Because saying that quantum theory is valid at sort of this scale. At least in what I read, I thought most physicists thinks it is, and that you cannot have these contradictions. Also, I think most physicists would say yes, indeed. If I perform a measurement, I'll get a certain outcome, and I cannot have sort of contradictions there. And consistency of the theory when applied by different observers also seems like super commonsensical to all the science we do and how we regard all theories of nature. So we have 3 assumptions that are quite commonsensical, and now this thought experiment tells us they cannot all be true.
Right.
Within the community, there was response to this thought experiment, and you, together with Renato Renner, wrote a response on that, right? Responding on criticisms. Could you sort of just briefly touch upon how this thought experiment was critiqued and what your response was to it? Yeah.
So most of the critics try to put restrictions on when can we apply logic in quantum mechanics. And the very common one is like, no, you should not be allowed to apply logic. I should not be allowed to think about what you think if I know that later someone like Wigner will come and measure your lab and destroy this, right? Because in this example, problems start happening when you have like these 2 super observers measuring the 2 labs. Right? And there's a few problems with this kind of criticism. One is that you cannot predict the future, right? You can always change this experiment, put the agents far away, space out their measurements enough or bring them closer, such that, you can put this final destructive measurement by Wigner in the far future. And what they're saying is essentially like, I cannot make predictions now if I don't know whether someone will come and measure my brain or measure your brain in 500 years, right?
Yeah.
Something like this.
Yeah.
Which renders this restriction a bit useless. Because if I just describe you an experiment, setting like in the next hour, please make a prediction. And then you ask me, okay, but in 2 hours, will someone come and measure my lab? Like, it's a bit strange to think that this would have an influence, right? That then you can move players apart in a way that this will like start bringing like violate relativity in the sense that like some action from the future is now. And
so that criticism would also apply to a lot of other different theories, and then also so it's a bit of sort of I don't know how you call that in philosophy, but it's this sort of argument that sort of doesn't really. Well, then you have a lot of other problems if this. Then you have a lot of
other problems. Yes. The other thing is also like, what is the line? What is classified as a destructive measurement by Wigner? Because again, measurement is just an evolution. It's just a physical evolution, right? Of a particular type.
Yeah.
And maybe these experiments have a very specific, very dramatic kind of measurement type of evolution where you see this terrible paradox. But there must be lots of intermediate cases where it does a measurement that's slightly different, or maybe it's a little bit more noisy, and still maybe you don't get like this contradiction, but you get some mismatch in probabilities of your predictions, right? You still get something that you wouldn't want. And it's very hard to put this line somewhere. Like, does my brain interacting with the environment and kind of dying, does this constitute a measurement? Would this be a measurement of this type? Like, can I not make predictions about whether the sun will die in a few millions of years just because of what will happen to my brain between now and then? All these things are not very practical. And to be maybe a bit more precise, there's lots of settings where we have partial information about how you model the world. Maybe in communication scenarios, like you send me a message and I try to guess something about you based on this message, for example. I should not need to know like exactly what's your view on the world, what do you model as a quantum system or whatnot. Like, if I need to know this for everything, if I need to keep track of all this context in a big chain, then again, the theory is not practical, right?
Yeah.
I pay a price in complexity.
Okay. Yeah. And so now I guess we're very deep into sort of technicalities, of course, because I asked you, so this is on me. We'll put the paper in below in the description so people can read sort of the criticism and your response to it. I guess the reason why I asked is because I was just wondering if sort of the consensus of the physics community is that this thought experiment is indeed something we need to take quite serious. And I think it is, right? Because we were both in Vienna, where Renato and Daniela were sort of they were awarded sort of the Dipole Repeller Award for Best Paper in Foundation of Quantum Physics for this paper, which to me signaled that, hey, the community is taking this quite serious, right?
Yeah, and there's other papers in like the one by Czeslaw Bruckner, the one by Eric, who were also there in Vienna at this interview, that have similar flavor, right?
Yeah, exactly.
Of being like, what we used to call facts, which are observations, are not absolute, and are in fact we can find these contradictions between observed facts between different people. So I think yes, there's quite a awareness in the community of this. It's still a very niche community within physics.
Yeah.
Yes.
And I mean, Eric Cavalcanti calls himself a metaphysical experimentalist. So he already sort of owns sort of the metaphysics as saying, okay, these experiments enter the arena of metaphysics. There's a tension, right? Because as physicists, you're not philosophers, but you guys are doing these thought experiments that do enter sort of metaphysics, because we are now talking about sort of just ground assumptions about reality. Is it sort of is there an objective reality the same for all observers, or can we formulate theories that apply to this common shared reality, stuff like that? And this thought experiment places us, sort of confronts us that we cannot hold all these assumptions to be true. So then what guidelines do you have as a physicist, or how to navigate these assumptions then? Is it just a matter of preference to say, I will let go of sort of the consistency, or I want to let go that quantum theory doesn't apply at all these scales? How do you navigate that?
A tough question.
Sorry, I know.
So first of all, like I agree with what you said. This is like physics entering philosophy, and also that as physicists we are very unprepared for this. Like, you know, you do a whole degree in physics without having a single philosophy class or metaphysics or anything, and sometimes it would help just being a bit familiar with the kind of concepts that are treated there. So how do you navigate these things? So some of these assumptions can be tested, right? Like quantum mechanics applies at these scales. We can test it. It's like testing collapse theories, essentially, right?
Yeah.
Larger and larger superposition. So that's kind of
the experiment for now. Yeah, experimentalists are working on that, right? Seeing how to. Do you know where are we now? Is it sort of at the molecular level?
I think yes, small molecules. I mean.
Yeah. Okay, so we can keep on doing that test. Can we get to the level of an observer in a superposition?
Yeah. Exactly.
Okay, check.
Yes. The other ones of putting limitations on logic. Again, this is something we can test to some extent, because we can say, okay, I'll try this limitation. Say, I cannot think about your thoughts if we have incompatible Heisenberg cuts for some definition of incompatibility. I want to test this definition of what compatibility is, and then I can test this and see like how far I can go or not with this, right? And see, okay.
And sorry, just to be clear, when we talk about sort of these differences in Heisenberg cuts, it's sort of disagreement on where we put the boundary between quantum and classical, right?
Exactly.
So and so we can't say, okay, I'm not sort of. We have to have a sort of an agreement on where the cut is between classical and quantum. Yeah.
Because if we do, then we don't have this kind of paradoxes arising, like this specific kind of paradoxes. Of course, you still have contextuality and whatnot, but not this kind. Right? So this is one of the reasons. Maybe it's a good time to do a segue of why we wrote this paper with Renato and Simon Mathis and Nuria Nurgalieva called Thought Experiments in a Quantum Computer. So the idea is there is to like model a little program that can be run on a small quantum computer, like the circuit I showed, where you need to program all the assumptions that you put in.
Mm-hmm.
So you need to program how you model each agent as a quantum system, where they put the Heisenberg cut, what kind of logic they use, what interpretation of quantum theory they use, and then you can test this and see if you find a contradiction or not. Right? So this is kind of our way of trying to navigate, like to answer your question, try to navigate. How do you cope with this?
Yeah, that software is called Conundrum, right? You're working on it. Is it sort of working yet?
I mean, there's like a prototype version that is on GitHub. If people can download.
We'll put it down. Can we put it down in the description?
You can. I mean, it's not amazing. And it was programmed mostly by a very good master student we had at the time, Simon Mathis, and then we Nuria, and maybe a little bit I refined it a little bit.
But I mean, it's coding this, right?
It's coding this. So it's coding this.
Yeah. And then, so we now have like thought experiment software sort of to run these.
Essentially, yes. Yeah. And then it spits out whether it tells you what were the predictions of all the agents and if there's a contradiction or not, right? And then you can say, okay, now I want to add one more agent, or I want to change the protocol of what they measure.
This is cool stuff because it's basically sort of metaphysics software, because we now have, you can put in assumptions and play around with it, and you get contradictions and stuff. So this is really where physics and philosophy meets, right?
This is cool, yes.
Yeah. And are there sort of already preliminary findings coming out of Conundrum or working on this that lead you to say, okay, I put my bets on letting go this assumption, or I think we should keep this assumption about reality? What are your sort of thoughts there?
No, I mean, the results are kind of what we expected, because also what we tested is the things that we were more familiar with, right? So ideally we would have lots of people playing with this and telling us their insights and improving the software. But, of course we see, if you have a collapse theory, then you don't have any problem. You don't have any contradiction. Of course, collapse theories have other problems outside this program, right?
Yeah.
It also shows, yes, if you have many worlds, then again, you don't have, if you program the agents to believe in many worlds, then there's no contradiction in the results.
Then you can let go of that one, because in a many worlds scenario, as we said, sort of the fill, and if both have an okay where they should contradict, or we have a contradiction where they should agree, in a many worlds interpretation, that can go, because you're just on different
That's it.
branches,
and there's also like that Alice, when she does the first measurement, she thinks of herself like, oh yeah, I see this measurement outcome, but I am in a superposition of saying this and that.
Yeah.
And now I keep track of this.
Yeah.
Which is a fair enough assumption. And again, the price you pay here, and this is very clear also when you program it, is complexity. It's like, imagine every time you see something, you need to keep track that, I'm seeing this, but I'm actually a superposition of seeing this and that and that and that and that.
And talking about sort of these quantum classical divide and that the Heisenberg cut. So we have objective collapse, which says we will find sort of this objective point where to put the cut, and that's the same for all observers, right? And we have many worlds say there is no cut, basically, right? Because the wave function just branches off, and there's not this quantum classical divide. And then we have like these epistemic approaches that do say it's really up to the observer to put the cut. Is that a way to say?
Right, depending on the epistemic approach you have.
Yeah.
I mean, many worlds also says that many worlds does not deny that you have a subjective experience of seeing one thing, but it says,
and
it's
just
an
for
illusion,
people to,
right?
again, I guess good to just sort of epistemic approaches. What are we talking about? Sort of epistemic interpretations of quantum theory.
Yeah, this is like quantum theory is about our knowledge.
Yeah.
Or maybe one of the most radical examples is cubism, where like quantum theory is like a tool that I use to navigate this world that helps me make predictions to win bets about the like outcome measurements of something.
And it doesn't tell me what I'm measuring, and it doesn't tell me what measurement I will get. It's just me betting in the universe of
which is fair enough, right?
Yeah.
We cannot really say more than that. But the problem is that, it's a relatively recent theory. It had not, I don't think it had been like really confronted before, this kind of experiments with, it's not just about my knowledge, but now how do I combine this? I need to take into account the point of view of other people.
Yeah.
right? So for this, it has a problem here. If you just wanted to apply like the vanilla version of this theory, it would be, Wigner only can reason from his point of view. He should not be allowed to like take this thing lying around like Alice and treat her as another agent and think of her as an agent and reason through her.
Yeah.
Right? Which again, fair enough, then you don't get a contradiction. But then there's also lots of other experiments you cannot do. Like, I don't know, if you're trying to predict the behavior of someone based on the result of some quantum measurement.
Yeah.
Then like cubism would not be the right tool to do this. Yeah.
So cubism has a hard time to sort of restore a common shared reality in a sense. So it does give you a way to explain these contradictions, because it's that just different observers using the theory.
Yeah, and you don't combine them. You just don't combine them.
Yeah, just don't combine them. You have your own truth. But if we want to sort of restore sort of a common reality, it has a difficulty.
Yeah, and also like you don't go very far if.
But what puzzles me a bit, Lídia, is that when we sat down in Vienna with Renato, he only later I read that in this Quanta magazine article that he initially thought that this thought experiment was sort of favoring many worlds. Let's say, okay, to account for this weird paradox, this seems to be most compatible or with a many worlds interpretation. And then later on, when I interviewed him in Vienna, when you were present there, right, he was pretty outspoken on the fact that he said, no, I really think these epistemic approaches and interpretations are the way forward. And not in a cubist sense, perhaps, but still. So I found it really very interesting. Have you had discussions with him on this, or what do you think?
A little bit over the years, but again, our opinions change.
Yeah, maybe. But what are your thoughts? So would you say? Can we even say that it doesn't favor anything, because it just tells us what we cannot be true at the same time, but still sort of
correct. I mean, it's not even about what cannot be true. I don't think quantum mechanics as a theory, as a tool, like in the same way that thermodynamics is a tool to help us build trains.
Yeah.
Quantum mechanics is a tool to help us, make predictions about a thing going on that we can witness. But in that sense, I'm more in the epistemic thing. But I also think that, every theory, it's like this Gödel incompleteness theorems. Every theory, at some point, if you find like a self-referential problem, you'll get to a paradox. Right? This also happens. There's some funny examples that I don't remember in classical mechanics, where you find this paradox and then the solution turns out to be like a quantum phenomena.
Yeah.
But like even every logical system, you make something that's kind of self-referential, and you find, and it's a paradox. It's just a limitation on logic.
Does it?
Right? And this is, in a way, it is, right? Because it's kind of quantum mechanics describing itself. Like the observer through this long chain is kind of describing itself as a quantum system, and that's where we hit.
Who wrote that paper again? Sort of quantum mechanics cannot sort of describe. Is this also Renato, or
this is the title of the original paper by Renato and Daniela?
Yeah, exactly. Cannot consistently describe how to use itself. So it's just this Gödel incompleteness thing. So it points in the end to the incompleteness of quantum mechanics, then, perhaps.
Yeah, which is not surprising, right? Because any theory is incomplete in this way. Any theory that tries to be universal has to be incomplete. So Nuria Nurgalieva, my co-author, her PhD thesis is exactly on this, and comparing this to other types of paradoxes. Like even like the simplest example is this sentence is false, right? If you try to assign a truth value to this sentence, then if it's true, then it's false. If it's false, then it's true. You cannot do this. And this is like a more complicated example of this, where you needed a lot of technicalities to kind of reach the same conclusion,
funny,
right?
In the end, sort of this sentence is false.
Yeah.
But I did think that quantum mechanics, because also a bit sort of physics history, but I mean, Einstein said the theory is not complete, and he came up with away why he thought so, the sort of the EPR paper, and then we had John Stuart Bell putting it to the test, and he did not prove it is complete, but he definitely did prove that it is not incomplete in the way Einstein thought it was incomplete, because Einstein thought of these local hidden variables, right? That we but those are ruled out. So I thought that physics was very much sort of on the page that quantum theory is sort of our most complete theory of reality.
I mean, we know it has some problems at some levels, like when it enters in conflict with general relativity.
Yeah.
We're only just, I mean, it's relatively recent, the field of studying what is a reference frame in quantum mechanics. So when you say spin is up relative to what? It means that, like, oh, we have something else that we use as a big magnet that this defines direction up. This big magnet is also a quantum system. What happens now if we play with this?
Yeah.
Right, so I think there's still a lot to explore in quantum mechanics. There are many no-go theorems for incompleteness in the sense that you meant, like ruling out many classes of hidden variables. This exists more and more. Of course, all of these theorems bring in other assumptions with them. Yeah, but this is a different type of incompleteness. So it's like the Gödel type of incompleteness. Like, we can find sentences within this theory that cannot be proven true or false. That's it. I mean, does it bring problems to us? I guess this is more like, does it have practical applications that could be problematic already, right? And this is something that people are starting to explore now. So can we take this kind of no-go theorems and now find a practical scenario? Maybe like instead of 4 observers, you have 4 little quantum computers. And if they reach these contradictory conclusions, like, can this result in problems? Like, can we find a game such that then this really results in problems? Can you find a scenario where this is...
We don't know yet.
I think this is still active research, yes.
Yeah, but it might. And that's where I think, as a storyteller or sort of science fiction mind, I do think that's very, very interesting, because if this would apply, so we could see this, then we would need 4 quantum computers or 2. Just Alice and Bob in their box would be a quantum computer.
This would be an example, yes. You can also think of Ursula and Wigner, the quantum computers, and Alice and Bob are like sub-parts of this quantum computers.
Check. Like
measuring a little quantum memory that...
Yeah.
And...
But then we would have like a node of 2 quantum computers in the future that we use for stuff, and then in 1/12 of the cases, sort of the logic breaks down.
Something like this, yes. But again...
Yeah.
It's a fun project for someone to take in. It's also very... a broad project of like, okay, now try to find a problem with this,
But I mean, it is sort of the work, because now it might be still science fiction, but thinking about the work of John Stuart Bell, which at that time was also thought of as just sort of philosophical or metaphysical, but then it led to quantum information and the quantum computer, right? So why wouldn't this lead, for instance, to a breakthrough technology, or perhaps like a big fundamental problem in quantum computing,
right?
When we combine quantum computers.
Yeah, this is why we need more funding for fundamental research. So for example, Bell's tests have lots of applications in cryptography, where you want to, because like this lack of hidden variables, like this lack of like nobody could have predicted what these things could be, also tell you that it's a way for 2 players to create something truly random between them that they can test, that no adversary can check, right? So it can be used in cryptography. And here we don't know. So the answer is that we simply don't know. It makes me worried a little bit that if you try to imbue logic in quantum computers, that maybe we'll reach some kind of problem like this, and it would be a cool project to investigate how. Yes.
It seems pretty. It's cool, and it's eerie in a sense that it breaks down, and that it would be sort of a huge anomaly, I think, in just the whole paradigm of computation if it does break down.
Right.
Yeah. Yeah, in Vienna, when we talked about it with Renato, Czaslaw, and Eric in a previous video, they all said this is like crazy for us too, because it was sort of an extra layer of weirdness, of craziness, in addition to Bell's theorem that already tells us that we cannot have sort of local realism and sort of freedom of experiment, that we cannot hold these assumptions true at the same time. So what is the addition here that makes it extra weird?
So the thing that it adds is like, oh, look, if like Bell's theorem does not disprove observations are facts and facts are universal. We can tell of this in Bell's theorem. Like you have these two agents far away, they measure their spins. True, universal. Like the spins are now spin out. It's a fact of the world, right?
Yeah, it might not be local, but then it's a fact of the world.
And I mean, and one way to check is then go and ask them.
Yeah.
Right. And what this experiment tells is like, no, there's no common experience of reality. Okay, I don't think facts of the world is a very useful expression because we only have our observations to go by.
Yeah.
So like even if I say like, okay, forget about facts of the world, but our observations are consistent, right?
Yeah.
I look at this apple and it's red, and you also see it being red, right?
Yeah,
and and this is like we can find situations where like we really have a radically incompatible observation of reality. Even when we're using the same physical theory, okay, we're applying it to different domains, but like the facts are really incompatible. Right? Like Alice really predicted 100% probability that you'll measure fail, and you measured okay.
Yeah.
Right? So this is the extra layer of strangeness. If you're very attached to, there must be a common reality that we are, like, science is a way to get to this common reality, right?
Yeah.
But one way to look at it is like, we only get to this common reality by kind of talking to each other, by correlations, by diffusing through the environment.
By performing measurements and talking.
By performing measurements, by having like the molecules of air escaping your lab and coming here, right? Correlations is what gives us a common reality. This is currently the way I like to.
And would you agree that just sort of this is sort of more on a sort of philosophy note that a common physical reality, we're talking about physical properties that are common, because there could be something underneath it all that still is very objective, observer independent, but it's just not sort of physical or...
Right, so there could be something underneath it all, right?
Yeah.
So you can model everyone in this experiment as a quantum system and have like the global Schrödinger equation evolving this whole thing, right? So yeah, sure, we don't deny this, but this is not useful to us, right? Knowing God's view
that's
of
like
the universe evolving.
Purely metaphysics there. But
it's not just this, like it doesn't tell us anything about our experiences. You cannot have both like this outside view and know what people are experiencing inside the experiment, right? If you want to have this, if I want to reason with the things I see in the lab or with the things I see around me, I look at you like photons hitting my eyes, quantum, this is a quantum process, right? If I want to reason with this, then I need to necessarily take an Heisenberg cut somewhere, right? Take my perspective.
Yeah.
Right?
Bernardo would say I have to dissociate, or sort of there has to be a dissociation. It seems like it's another way philosophically to talk about sort of a cut between two personalities. This is fascinating because I remember when we had a pre-discussion of this conversation and talking about what it all means, you had this metaphor of this God's eye view. Like I can give you Super Mario on a disc, here's the game, and then there you have it. That's the universe. But we both know that the game is to be played and to be in it and to have these different perspectives, and that's the experience of the game.
Yes,
is that's what you're hitting at here, right?
Yes, It's also one criticism that many of the shut up and calculate kind of physicists say of this is like, you should not be allowed to take the point of view of these little agents inside their boxes. Like, just apply the Schrödinger equation from the outside. You see everything evolving, like, beautiful.
Yeah.
but we are the little people inside the boxes.
Yeah, exactly. And that doesn't tell us anything in the end. Yeah.
Like, we are not experiencing the video game from the perspective of the developer outside reading the code. We are inside the game.
Yeah. This is so interesting. Yeah, and also, I mean, the outside view. Then, how do you say that? It's not computationally reducible in a sense. You cannot sort of. It has to be played out, right? It has to sort of render itself out. You cannot. I had a conversation with a complexity scientist. James Gladfelder about sort of information and the game of life, that Conway game of life with simple rules. You get to sort of very complex, you get to like Avatar and whole worlds, and you just started out with this simple grid with just super simple rules. But I think sort of the philosophical takeaway from Conway's game of life is that there's no way where you can get from the initial state to that sort of and complexity that the game will give you if you just render it out. You have to go through that. You have to go through the computations. You could maybe speed that up with a supercomputer, but there's no way. But I might be misunderstanding this. There's no way algorithmically to sort of
to
know
predict
from
what
state.
Goes from.
Exactly, you have to go through it, right?
Yeah. So I don't know about this particular example, but I think there's many examples of computational problems that have this property. It's already maximally efficient. You cannot. Predict without kind of iterating it. Yes. And the same can be true.
Yeah. But so you basically said you are not sort of, you say, okay, I'm not a philosopher, and we are, as physicists, perhaps a little bit unequipped we don't have the right tools to strongly distinguish between these assumptions, which one is the most plausible. But hearing you talk, it does. Yeah, so you do seem to favor more of these epistemic interpretations, or are you just...
so. So I think all theories are, because of the way we are built, because of the way we interact with the world, all theories are about our interactions.
Yeah.
Right. Even whenever we talk about causality, cause and effect, like even in astronomy, say. When I say, there's this gravitational law and this is why the planets move around this, it's not like I'm going around and like changing the planets unless I'm running a simulation, which can be done. But we do think about it like, what would happen if this planet wasn't here, right? Which is a kind of intervention. We might not be doing it in person, but it's still about our relation, like what we could do. So I think this applies to, I now think that this applies to physics in general, but also like to other physical theories. So in that sense, yes, everything is about our knowledge. From our perspective.
And how would it be different if, say, the objective collapse is true and not this epistemic approach, that it is an objective theory about an objective world out there, or the many worlds is true, that we are just on different branches of the wave function and there is no collapse and it's basically all present.
Okay, if the objective collapse is true, that's easier.
Yeah, check. What would that mean?
Okay, then you'd not get a paradox in this situation, right? So there's something we can test eventually, like as we superpose large and larger systems.
Yeah.
And then we can, at what scale does this objective collapse happen? Is it like 5 kilograms? Okay, so then can a small cat be an observer? Okay, or like I miniaturize you, and now you don't suffer this objective collapse, and I run the experiment and still have the same problem, right?
Yeah.
Or it could be, I don't know, a collapse in consciousness and whatever when you do a measurement. Then fine, then okay, you don't have this specific problem. You still have many other questions to answer about your physics and how it interacts with the other branches of physics.
Yeah, what's the biggest one then? Sorry, I guess you just mentioned. But...
So with collapse, it has some problems with relativity, being consistent with relativity at some scale, for example. And also needs to justify where is this collapse coming from, like why is quantum mechanics breaking down at some scale?
Yeah.
Yes, but still I think that eventually we would find, in whatever physical theory, I think we'd find a paradox like this. So if many worlds was true, then I think again, like, fine. What does this tell us? What are you going to do with this information? Because I still need to use quantum theory from my perspective of seeing this outcome. If I need to keep track of all the branches of the wave function, it's not practical. Like, I cannot do this with finite resources. I'll very quickly run out of memory. So, okay, yes, many worlds is true. Everything that's possible to happen happens. Like, so much. Like, also, what a boring world it is. A world where everything happens.
It only wouldn't be boring if I could switch those branches, but that's unfortunately not. That's not how it works, right?
I feel sometimes I just have like fantasies of divorced dads.
What of divorced
dads? So like people who regret their choices and like, okay, so what if live with your bad decisions? It's okay. We all do it. No, I have a friend who's a physicist called Johan Berg.
Yeah.
Who says that a world where everything happens is as boring as a world where nothing happens. So
that's one to think about. Yeah.
No reversibility, no consequences. It's like,
yeah. Which makes me, this is sort of really segue, but free will, do you sort of have do you believe in free will?
I believe in relative free will. In the sense like, you cannot predict my actions. What is the source of free will? I mean, is everything I'm made of? If someone knew everything I'm made of, which, there's many arguments of, the complexity of this is to burn through every hard drive. You just can't do it. But then they would be able to predict what I do. But does this take away from my experience of thinking I have free will? Like, I don't know, we were offline, we were talking about children, right?
Yeah.
And like, when they're hungry, you can 100% determine that they'll be cranky.
Yeah.
But they still have their subjective experience of, like, no, it's my...
No, I'm reasonable. I'm being reasonable.
Yeah. And let them have this experience, right?
Yeah.
So I'm kind of at peace with like, okay,
yeah.
If there's a super observer who can predict everything I'm gonna do, like, it's okay.
Yeah. It's funny. It's almost as if sort of physics is now sort of confirming this sort of cliche, commonly held thing where people say every person has their own reality, right? And has somehow and we all know that's not true. There are sort of objective facts in the world. So I'm a bit puzzled here because we still live in a macroscopic world where it just seems to be a commonly shared world that stays the same, but is observer independent. Is that just because we're then just completely entangled? Is that the way to put it?
That's I mean, this experiment was it's kind of very fine-tuned, very designed to reach this outcome, like to find this contradiction. But I think most of it is. It's also it's what allows us to have a shared experience of time passing, is that we share systems like the Earth, the Sun, the thing that we use as clocks in practice. Yeah. It's like everything that gives us a shared experience of a shared reality that we construct together, it's correlations. Yeah.
We need these tools to construct it.
Yeah.
But that doesn't mean that it's really there outside of us or independent of us.
Yeah, I mean, personally, I believe that there is a world. that I'm not like in a box creating.
Yeah, you're not.
I'm not that smart.
You're not a solipsist. Philosophers call a solipsist. No, okay, check.
But like all we can access is our experience of the world. Like what Bernardo says of like we're seeing stuff through a screen and we're interacting with the world through a screen. And what gives us like this idea of like, we're interacting with the same thing is really this correlations between us.
Check. Yeah. And so in your work as a physicist, you are at peace with the fact that your work is very much about how that screen works, how that interacts, and not so much about what it really points to or what that really is, which is still metaphysics in the end.
I guess.
Whereas
I don't know, because some other things I do in my work is like thinking, okay, what if instead of living in a quantum mechanical universe, we lived in a stranger universe or in a simpler universe? So there's different physical theories that you can make up.
Yeah.
And now see, okay, how would agents experience the world there? How would this be different? And this maybe gives us some clue of like,
That's interesting though, because I'd say, okay, we know we live in a quantum mechanical world, right? We have established that experimentally, at least microscopically.
As far as we can tell, it's a very good theory, yes.
And that world is pretty weird, but still also commonsensical. How would it be? What would a weirder world look like? What would a simpler world look like if you just said to think about that? So I'm curious here.
So I think we'll touch this in some of the other interviews. What I mean by a weirder world is like one with correlations stronger than quantum entanglement, for example. Where, you remember we talked about Bell's theorem, how it can be formulated as a game, but like classically you can only win it with like 3/4 probability. And like with a quantum strategy, you can win it like 80-something%. And you could imagine like, oh, what would be like a black box view of a world that would make you always win this game? Like correlations, like non-locality even stronger than what we have in quantum theory, right? And turns out like that this kind of worlds, if you impose this condition, like, okay, it needs to be stranger than quantum in this very specific thing, then it restricts like the dynamics of this. Just these correlations restrict like the dynamics of systems, like the physics of what kind of physics are possible there. And then it also restricts how we model agents and if you find these paradoxes and so on. Yeah. So this is one direction.
I'm super curious there because do you have any clue how that would be for an observer in such a weirder world experientially? I mean, this is science fiction, of course, but
yeah, it is science fiction. But we looked into this. So there's a paper with Núria and Villasine, where we looked precisely at this world. And so one thing that is not stable there is the notion of a system. Of like, I treat this thing as a system, as an observer, but then later on I need to kind of combine it with something else, and now this whole thing is an observer. So it's cool. Things that we take for granted in quantum mechanics, like, I call this a system. Right? Which is, again, it's a choice. It's a choice of boundary that I do. Yeah. Like, this choice is not kind of stable in other theories.
It's fluid, and it's fluid.
It's fluid, yes.
Yeah. Would that also mean, because observers are systems in the end, that sort of observerhood is also fluid then?
Yeah, in a way. It's funny.
So your boundary between you and is just more fluid.
And so in that kind of world, you can still find this kind of paradoxes. And then we studied also simpler worlds, so like this kind of hidden variable worlds that simulate some of the properties of quantum mechanics, but they are classical worlds. Like, all particles have a definite position and momentum. We just don't know. There's just like enforced ignorance. This is, for example, Speck and Stoy theory. In that model, what would it be like to be an agent in such a world? And then what we find is that it's very hard to then make decisions for agents to like take information and then, depending on this information, making some decision and taking some action. This is extremely, extremely hard.
Why exactly? Why is it hard?
It could have to do with the mechanics of this particular world, where like it's kind of all probabilities are 50-50 to some extent. So everything needs to be like, you cannot kind of bias your decisions more one way or another. It would be like
a very black and white world.
Yeah, it's a very black and white world. And then you don't find this paradoxes, because it's a classical theory, so you're not expected. But also you're very limited what you'd be as an agent. So you can play around with these things.
This is just really cool, because this is of course very technical how you construct these worlds, but it's just you can do this. So how do you do that? Is this all math?
So other people have studied. It's a very fruitful, I think, field of research to try to understand why is the world quantum mechanical. What we do is we test alternatives. Right?
Okay.
There's different ways to test alternatives. One very popular one is like, okay, treat everything as black boxes. Like maybe there's some electrons in a box and I shoot some lasers, but I just think of like, there's some buttons I push, I get some outcomes. I study the probabilities, the frequencies of these things.
Yeah.
And now if you put quantum systems inside this gives you some probabilities. If you put a classical system inside this, you get different probabilities, right? But then you can like forget what's inside and just say, okay, what if now I want to see if I get different types of probabilities? So I fix the outcomes, and then I try to kind of reverse engineer what's inside the box. So this is a big field of research, like called like generalized probability theories that people. It's a way to study. It's like one direction to study how the world could be different from quantum theory.
And what will the what's the sort of the this is maybe a sort of not meant as an insult, but what's the relevance of coming up with these different worlds for physics? Where does it become relevant for sort of the foundations of physics?
So many things. So one would be that maybe we find something that is very close to quantum theory, right, where the probabilities are like almost indistinguishable from what we can see, but which has much more intuitive properties, right? And then this would be, oh, interesting. Maybe we should study this thing instead, right? Or maybe we try to find, or maybe this leads us to try to find an experiment to determine, like, are we in the quantum mechanical world or are we in this other world, right? Another direction of research people do is like, quantum theory is such an elegant theory, right? But it's derived from 4 or 5 axioms that are all mathematical. Like, states are vectors in a Hilbert space, a measurement is... And this is... It's not very satisfying, right? Because it doesn't tell us much about the nature. So there's ways of... directions of research where you just try to find more intuitive axioms that maybe they're more physical. And then from here, try to derive quantum mechanics. And then you can say, oh, what happens if I change this a little bit? Yeah. Now I get a different class of theories. And why are we not there? Like, why is the world like this? So this is kind of the...
Yeah, I think this is all just very inspiring sort of as a storyteller and giving ideas for science fiction, right? We know the science fiction around sort of more many worlds kind of theories, that you have these alternative world lines, but then you end up in pretty much the same world as we know, but just different, that I can have like a different life and it's all possible at the same time and can maybe switch those. But it seems to me that the stuff you're working on could lead to even more exotic sort of science fiction. Do you have any ideas here?
Yeah, I think it's a very good question. I think quantum theory has the potential to inspire even more interesting science fiction. This is one of the examples. I don't know. In a non-science fiction thing, I've seen someone almost try to justify an affair with things like, oh, if they don't know, then
so that's how you physicist how you use this theory.
Like, come on, you cannot control correlations. It's not this, right? But yeah, no, there's very rich terrain here for stories that are exactly this, right? So we had alternative realities or experience of realities until we meet, and then what happens? Like, do we forget our previous experience, or do we? Yeah. I think it's something cool to explore that also has not been very explored. I have a friend who's a physicist, Nicole Junger-Halpern. Every year, she did it once, I think she'll do it again. She runs a contest of like short stories inspired by quantum theory.
Cool.
So like to give us something
need to
like
go in those. Yeah.
Yes. So, I don't know, but I think there's potential here.
And because I think many people, of course, at the Essentia Foundation, we're about sort of analytic idealism, consciousness being fundamental, and idealism is associated mostly worldwide with people who are religious or spiritual, right? That's sort of the idealism we know that is sort of just ancient, coming from all these traditions, and we approach it analytically, and that limits what we can or cannot say. So if you ask me or Bernardo, or does God exist, I'll say yes, but not in the way you commonly think about God as delivered in these ancient texts and stuff. So you have all these limits because you want to approach it analytically, right? But I do think that quantum mechanics, for instance, inspires especially people who have this inclination, who are sort of spiritual, to say, see, everything's about consciousness. I can sort of just manifest my own world if I truly believe in things. And you have to sort of like this whole scene of manifestation. And they all sort of run away with quantum theory. And then, of course, physicists are annoyed by that. We even had this movie, What the Bleep Do We Know, like, which really popularized quantum mechanics. I think it's 20 or 25 years ago, but it just went off the rails because it had these fragments in it basically saying that if you want a Ferrari and just focus on it, you manifest, stuff like that. Yeah. But what's sort of the way how all of this informs you, or do you think how it can inform people on a meaning level? Can physics tell us anything there? Or,
yes, I think it's told me some things. One thing is that we draw these boundaries around us. We try to classify the world because that's how humans survive. Like, we find patterns and we classify things. Like, from this point on, it counts as a mammal. Before it doesn't, right? But nature doesn't care about these boundaries, right? Like the Heisenberg cut. I treat these photons as quantum mechanical, but not the ones that are entering my eyes. Yeah. Like this idea of like, be aware that whenever you try to classify something, whenever you try to draw a boundary, that someone else might be drawing it differently, and that these things are not. So one example, for example, when I teach the double slit experiment, I'm like, oh, is light a particle? Is it a wave? Now, because I have quite a young generation of students now, I say, look, there is like people saying that you have to be a man or a woman. Like, we created these categories based on some biology, but like they're not always useful. Nature is more diverse than this. It's like, we said, we divide the world into particles and waves, but like light is something else that has properties of both, right? So I think physics has really informed me in this. Maybe I had this inclination already, right? I mean, I'm biased too. And that's why this is the lesson I see in physics.
Yeah.
But yes, the main thing is really like, for me, it's like, more and more things are subjective and relational. UCMS, I see my organized chaos. I know exactly where I put this thing. And that this I think it has helped me going through life. Yes, like there's no universal bad thing. Like, from the perspective of the bad person, they actually have their own interests and views and stuff, and like this helps me connect to people when
that's like this non-dualist notion coming from physics here, that you say okay, there's no objective way. To me sort of that was, it's funny because I was brought up religious, and in religion, in Christianity, I was brought up was quite dualistic in a sense. Definitely when it comes to good and evil, and making that like very, very objective, right? Like God and Satan, and it's like pretty clear divide, and it's transcendent evil and stuff like that. And I still, when I'm entering into discussions with friends who are still more on that page, no, there's like pure evil, I'm much more like, no, it's us sort of having to sync and navigate this. We create this moral landscape as mammals, as humans, and that doesn't make it's absolutely real for us.
Yes.
And right, but in the end, if physics also teaches us that there's no outside way to just objectively say this is the case for everyone, I can map that perfectly well with sort of a non-dualist way of looking also ethically at the world.
Yes, yes. Which is not like a free-for-all, right? It's not like all the options are true. Like, we have correlations. There's a reason why we consider some things to be bad as a decision that we make together, right?
Yeah.
It's not like, genocide is okay. It's not this that I'm saying, right?
That's
just
not, absolutely not, no. So, and were you brought up religious, if I may ask?
So, no, not my parents. I mean, I was brought up in a Catholic country, but... Portugal in, I think, still recent. I can still call it recent years. but my parents are not religious, but they're very artistic and culturally inclined people. But like, I went through a very religious phase when I was 6, 7, 8 years
old.
old.
Oh, that's interesting.
I was very.
That's pretty. You were devout then. Yeah.
Yeah, I was like comparing different versions of the Bible. And
wow.
Wow. But then at some point, it's like this is not. There's all these inconsistencies. It's not just inconsistencies. It's like it's a very limited way of look at the world, and you look at different religions and learn a little bit from everything, and a few points. One, I think is very useful for scientists working on foundations. I mean, for everyone in general, but for scientists working on foundations to be aware of their own relationship with faith, religion, and their own mortality. Because these things kind of sneak up into your research. And it's good to be aware of this, of like, I don't know, I'm really afraid of death. I don't want to think about it. And then now suddenly I believe in many worlds in which, there's always a branch of quantum theory.
Are you
not
really?
me.
No, I know. Okay, but you really think that sort of these psychological mechanisms slip into even...
I think they do a little bit. That
yeah.
I favor some view of the world because of the way. Why was Einstein so upset about quantum mechanics? I mean, I don't think it's about his view with mortality, but about some way you're brought up and you think about how the world should work that you might not be aware of. And in foundations, I see many people believing something because they want it to be true, and then if you dig in enough, like sometimes they're afraid to die. And this maybe explains a bit of the generational.
Yeah, that's super. It's super interesting. I think it's just being brutally honest with how the human mind. If we say modeling the agent in the system, we have to also model in metaphysical assumptions or sort of psychological mechanisms that just play into how you want the world to be.
Yeah,
but then in the end, we do have this stick that can ground us, which we call mathematics then, right? Or still...
Yeah, I mean, of course, yes.
Okay.
Yeah. But it's about like, you have a no-go theorem now, which assumptions do you prefer, or which ones are you happy to let go of? Or which directions do you explore from there? Sometimes like all these beliefs we have kind of
and how does it... But how, if I may ask, how does it play into your view on your being a human and your mortality? Does your work in some sense sort of inform you about this? Is that
yeah, actually
yeah
I mean, this was at university that I learned about what are waves, like think of a Mexican wave in a football stadium, like people get up and do this and then the wave propagates, right? Matter moves locally, but the wave is actually propagating.
Oh yeah, that's nice. Yeah,
it's like, this is the perfect metaphor for life and death. I'm happy. I'm not going anywhere else. It's like, okay, I'm here. I do my own thing. I move a little bit, and then I die. And I'm part of the big wave, and like the wave propagates. And this doesn't mean like my spirit goes somewhere, but like my actions have consequences in the world, and this moves on, and I'm okay with this. Like, we lose my point of view when I die. Or I will lose my point of view. Like, other people don't have my point of view to start with, right?
But the information associated with it, or the correlations associated with it, in some sense, sort of will survive you. Or
like in the sense that I remember my grandmother as if she was here, right? And her actions have still an influence.
That's beautiful.
In my life, and
it's beautiful. It's beautiful. Yeah.
But I'm lucky in having the kind of brain that is okay with this belief, right? Many people cannot help it, and and you really need something else to comfort you. And it's just good to be aware of like, what tools am I using? To comfort myself, and is this also influencing my work, which is okay. I just should be aware of it all. This. Yeah.
Wow, it gets so subjective, but in a sense that how to put it is, I think closer to truth than thinking that there's this objective way to go about here. I agree with you that I also think I'm more inclined to thinking that I play this role that I don't understand yet, and I might dissolve, but it has had its function for the whole. What it makes me think is that we're talking about Heisenberg cut and what's quantum and what's classical, but as persons we also are making this cut, right? This is the cut I place sort of literally here, and that's my cut. And I just think that it's all classical, or say I'm quantum and you're classical. How can I know? But hearing you, and if there's no objective way to make that cut, also sort of feels very human and humbling that I cannot know sort of the larger whole I'm a part of, right? And that the cut I make is very subjective, even though I experience it to be very real. That's what it sort of is telling to me.
Yes. Also, like the boundary between what is I. I mean, I is a convention, right? That I say, okay, maybe like there's feelings in this body. This is where I cut it. And but this is a convention, and there's been others throughout history, and and it's something that we use for applying responsibility, or for punishing people, or rewarding people, or for whatever. That has some social function, right? But it's this boundary is in principle like motel, and it's just where we put it.
And it's just super cool that you're working on modeling sort of that all, right? We are later this year, we will host a conference together where you are also involved and co-organizing with us on integrated information theory, which is also a theory that tries to model the boundaries of consciousness, or sort of where a whole, sort of a conscious whole, how we can sort of map that. And that I think is pretty cool, that we can sort of say something meaningful about how at least people experience being a conscious unit, so to speak. And I'm still puzzled, and this is also science fiction. I mean, I spoke to Christoph Koch, who says, okay, when you get to sort of a new maximum integrated information, so he said if I connect the brains of the two of us, and you get to this maximum of new integrated information, there will be a new subject, and it will also that both Lídia and Hans at that moment cease to exist, and you have this one bigger brain. So that might be true, but it also might be true that perhaps the bacteria, the cells in my bodies have some form of consciousness that I'm not aware of, and I'm just experiencing this whole larger meta consciousness. These are all sort of the questions that I'm very much open to, and I just think it's cool that we now are finding ways or trying to explore it, right?
It's cool.
Okay, Lídia, thanks so much for this conversation. I really enjoyed it, and I really like how we got from quantum computing and these thought experiments to sort of more questions about the meaning of life. Just thank you very much. It's great for Essentia to have you as a research fellow working on all of this. And we have much more content also with you co-interviewing with me people we visited in the Vienna Foundations of Physics conference. And we will, of course, have a conference on IIT later this year. So there's more content with you coming up. And for you watching this, we will put in the descriptions below links to papers of Lídia and the scientists and physicists she referred to. And please leave questions, because Lídia and I will be filming more this year, so we can touch upon your questions and try and answer them. Thanks so much for watching.
Interpretations inflict unnecessary suffering. How might different ways of thinking transform the same situation? What mental models limit your perception of possibility? And what mental models can truly elevate your life to higher levels? How does your attention influence or create what appears most real and significant? When you are aware of the mental dimension of experience, you discover that many prisons exist primarily in thought and can be transformed through the same medium. Rulers don't want you to know, but we are fragments of divinity. We walk the earth, forgetting our origin, yet we carry the spark. This final principle may appear grandiose, even blasphemous from certain perspectives. Yet, across all wisdom traditions, it appears as a consistent recognition that human consciousness is part of the divine nature, that we are not only physical beings having occasional spiritual experiences, but spiritual beings having temporary physical experiences. We are all manifestations of the same supreme oneness. Thus, we are all gods. The Vedantic tradition declares Aham Brahmasmi, which means I am Brahman, the ultimate reality. The mystical Christian recognizes that the kingdom of God is within you. The Hermetic tradition states, as above, so below, the human microcosm reflects the divine macrocosm. However, keep in mind that I am not trying to inflate your ego. That's the opposite of my intention. What I intend is to remind you of your essential nature and help you recognize it from now on. Spinoza, the brilliant lens grinder and philosopher, perceived all existence as expressions of a single divine substance. In his view, we are not separate from divinity, but particular manifestations of it, or modes of the infinite, expressing through finite form. Not God in the anthropomorphic sense, but in essence and substance. Consider the implications of this perspective. If we are manifestations of the divine, our creative capacity reflects this origin. Through consciousness, will, and action, we participate in creating reality. Our thoughts, words, and deeds help create it. We are not passive observers, but active participants in the unfolding cosmos. As Alan Watts beautifully expressed, to know that you are God is another way of saying that you feel completely one with this universe. This principle also doesn't justify narcissistic entitlement. Quite the opposite, it places a great responsibility on each consciousness. If our thoughts and actions participate in creating reality, both personally and collectively, we bear cosmic responsibility for their quality and direction, as divine capacity requires divine awareness. Think about what happens when we forget this principle. We perceive ourselves as isolated fragments in a mechanical universe, mere products of chance and necessity, disconnected from source and purpose, resentful, envious, closed, unripened, running after the wrong keys. This amnesia creates an existential alienation and a spiritual homesickness that characterizes much of the modern suffering we feel. But the mystic minds offer processes for remembering divine nature. Meditation reveals the witness consciousness beyond personality. Contemplative prayer opens communion with the divine. Entheogenic ceremonies dissolve boundaries between self and cosmos. Looking at the ocean silently and admiring how wonderful it is to be able to be one with it here on Earth, and this reality. These are all great ways to remove the veils that obscure that precious essential nature. When we first understand and feel this reality, even momentarily, our minds change forever. Personal concerns don't disappear, but recontextualize within larger awareness. The dramas that consumed us reveal themselves as particular plays on a cosmic stage, which are significant yet not ultimate. The boundaries that seem so solid become permeable. The separations more apparent than real. The diversity more united than we initially were capable of seeing. This principle raises several ethical questions. If all beings share divine essence, how might we treat them differently? If consciousness itself is sacred, how might we engage our thoughts with greater reverence? If we participate in creating reality, what responsibility do we bear for its quality? This principle reframes human limitation. We remain finite expressions of the infinite, temporal manifestations of the eternal, conditioned vehicles of the unconditioned. The constraints of embodied existence remain while simultaneously participating in transcendent awareness. That's why we are gods, all of us. Carl Jung recognized this paradox in psychological terms. Individuation involves both differentiation of a unique personality and recognition of connection to the collective unconscious. We become most distinctly ourselves precisely as we recognize participation in something greater than personal identity. Quantum physicist Erwin Schrödinger concluded with an incredible statement: the total number of minds in the universe is one. This principle invites both contemplation and expression. We access divinity through stillness that reveals an essential awareness. We manifest divinity through creativity that expresses purpose. Neither alone is sufficient. Both receptivity and activity participate in God's plan. Ask yourself, what does it mean for you to possess a consciousness that is divine in nature? How does your creative capacity reflect cosmic creativity? What responsibility accompanies the power to shape reality through perception and action? What veils obscure recognition of your essential nature? Never forget that the recognition of your divine nature doesn't separate you from your humanity. Quite the contrary, it connects you more deeply to it. Human life suddenly becomes sacred in all of its forms when we realize that the same essence expresses through infinite forms. The divine is playing hide and seek with itself through the cosmic game of manifestation. When you think about it, we are not separate entities seeking God. We are God seeking ourselves. We've journeyed together through 12 principles that form the bedrock of a life worth living, 12 principles that demand embodiment, 12 immediate realities that await recognition. From controlling what we can control, to recognizing our divine nature, from integrating opposites to embracing patience, each principle forms part of a constellation that, when viewed as a whole, maps the territory of our potential. Each reveals an aspect of reality that, once seen, cannot be unseen. These principles aren't mine to give or yours to take. They belong to no one and everyone. They've been articulated by sages across millennia, rediscovered by seekers in every generation, and embodied by those who understand that true wisdom isn't theoretical, but practical. From Epictetus to Einstein, from Lao Tzu to Jung, from Buddha to Spinoza, the greatest minds converge on these fundamental patterns because truth recognizes itself. What makes these principles so powerful and so dangerous to conventional thinking is that they can't be compartmentalized. Each implies all the others. Each contains within it the seed of total transformation. You cannot truly apply just one without eventually encountering all of them, because reality is a unified field, not a fragmented collection. And of course, there are countless other principles you can now, hopefully, discover and implement with more ease. The question now is what you'll do with them. Knowledge without application remains sterile. Understanding without embodiment becomes another form of spiritual entertainment. The principles we've explored are living presences that inform every decision, every relationship, every moment of your existence, so put them into practice. I invite you to sit with these principles, metabolize them, do not quote them, but become them. The philosopher Heraclitus said that character is destiny. Similarly, these principles we explored, when integrated, don't just change your character but transform your destiny. This is why I create these explorations, not to add to the noise of information, but to create silence in which wisdom can be heard. Not to give you more, but to reveal what you already possess. Not to elevate myself, but to remind you of your height. If these revelations resonate with the truth you already know but may have forgotten, that is no coincidence. Truth recognizes itself across time and space. I should also point out that these principles are not about achieving perfection, but embracing wholeness. They don't promise the absence of suffering, but the transformation of it. They don't offer escape from reality, but deeper immersion in it. They don't separate you from the world, but connect you more profoundly to it. You should now sense a larger feeling of freedom. In a world fragmenting into specialized disciplines and isolated identities, these principles offer integration. In a culture obsessed with novelty, they offer timelessness. In a society driven by external validation, they reveal the sovereign power that has always resided within you. The ancient Hermetic axiom states, as above, so below, as within, so without. The principles we've explored operate at every scale of existence, from quantum fields to cosmic expansion, from neural networks to social systems, from individual psyches to collective consciousness. As a consequence, if you embody them in your life, you participate in the harmonization of all levels of reality. This is our destiny, but most of us don't know it yet. This is the great work that transforms base metals into gold, fragmentation into wholeness, unconsciousness into awareness. This is what you were born for. This is what awaits you when you awaken to the principles that have always guided those with eyes to see and hearts to understand. Until our paths cross again on the next exploration, may these principles illuminate your path as they have illuminated the paths of countless seekers before you, including myself. May they reveal to you the extraordinary being I know you've always been, waiting patiently to be recognized.
A model, so that's a symbolic representation of how consciousness works, which therefore must be different from how it actually works. Consciousness is one unified thing. You know, it's effectively indistinguishable from the concept of reality at large. It's all that exists, and it just is. That's stage 10. So hell yeah, nice one, we got to the end of the model. Now, where the hell did I actually get this model? Well, this model is a bit of my interpretation, and it's an integration of 2 or 3 different sources. One source in particular has kind of most of it, but I've taken little bits here and there from all over the place. First off, there was a psychological model constructed by a guy called Claire Graves, which produced an open-ended set of developmental levels. His approach was fairly scientific, although it did notably suffer from some sampling bias, so it wasn't exactly flipping the table on all of psychology or anything. Then there was spiral dynamics, which was a model which was developed out of Graves' work by 2 guys called Don Beck and Christopher Cohen. This was much more heavily criticized as being kind of ideological and a bit culty, but I still enjoyed looking into it, and the lower stages here do reflect that model a fair amount. Then there's Jane Lovinger, I think that's how you pronounce the name, who developed a theory of personality using a methodology of sentence completion tests, and she came up with a model called the stages of ego development, which were then further refined by someone called Suzanne Cook-Greuter, and that model has a lot of similarities with the kind of stages 6 through 10 of my model, and it also aligns with the kind of spiral dynamics models-ish. So I've just taken all of these, rejigged the terminology a bit, and created something kind of unified out of it to the best of my ability. Now, all these models and the methodologies they use have kind of varying levels of scientific validity. Like, some are pretty decent and some are pretty pseudoscience-y, so I'll just let it be your call as to whether you think any of them are valid or whether they're all garbage, or what you think of the model I've got on screen here, if you think that is great or if you think it's terrible. But I will admit, at least from an anecdotal perspective, this model here, like, I can personally believe that something like this is correct. In my head, it really does make sense, I think. Although I will say, I very much consider the details of this exact model to be essentially a work in progress. I don't consider this to be absolute and final and definite. Like, I've gone ahead and integrated things in a way that makes sense to me, but ultimately it's up to you if you want to reject this model. But I kind of like it, and it's very fun to think about at the very least. And it's fun to envision a future where we get to a point where we're trying to optimize impacts on the universe via, you know, whatever technology we have, like Dyson sphere-powered interstellar cybernetic genetic engineering nonsense, whatever it is that we come up with. And that's what society's trying to do. But then meanwhile, you know, maybe conservative thinkers aren't convinced by that, and they think we should use, I don't know, AI-powered supercomputers to use this whole systems thinking analysis to explore every conceivable viewpoint before we get too hasty. And then progressives in the society are trying to outdo each other with new, increasingly weird models of how reality works. Like, it's trippy and cool to think about how this might go. Of course, that does assume that things go pretty well. Now, I know I said that people just move up this model, but a society makes new people all the time, and a time of hardship can make it harder for a new generation to make their way up these stages. It's also technically possible to regress as an individual too. It pretty much has to be under kind of terrible life circumstances though, because that pushes you down into a more frantic, instinctual survival mode of looking at the world. So if you lose a job and you go through a divorce and some of your family members die and you fall out with all of your friends all at the same time, then yeah, you're at risk of devolving by a stage, maybe even 2 stages. Particularly if parts of you are still present at a lower stage, which is something worth mentioning too. It's not as if a person or a culture is entirely at one particular stage of development, and this is why this model is kind of delicate and nuanced. You could be 25% at stage 6, 50% at stage 5 and 25% at stage 4. Like, different aspects of a person can be more or less developed. Like, you know, you could have better cognition but lower emotional capacity, and your morals are somewhere in the middle, or whatever. But I find that way of trying to categorize the different aspects a bit vague though. Like, how many independent axes are there exactly? It's kind of up in the air. It'd be nice to come up with a more rigorous model of that aspect specifically, but I don't know. So I just kind of tend not to get too hung up on the details. I just feel out out where I'm mostly at when I'm looking at this model. I just try to not leave any obvious places of myself at lower stages. I've heard leftover remnants of your psyche left at lower stages being referred to as shadow aspects, which, damn, that sounds like a Yu-Gi-Oh card. A good way to make sure that that kind of thing doesn't happen is by fully exploring each stage before you try and move on. Again, this is why you can't really jump stages. You could easily spend 10 years at each stage from proto-irrational onwards to fully exhaust it. But when you do try to advance forward, and I know I've said this before, but I'll say it again, you can't jump stages. Just to help you out with this, like, most people will think of themselves as about 2 stages higher than they actually are, because you're going to either like the individualist mindset or the collectivist mindset, and being only 1 stage higher would put you in a position that you probably actively disagree with right now. But, like, not everyone will overestimate themselves, some people will underestimate where they are, but most people go over. So just notice that statistically speaking, you're probably lower down on the model than you would like to think that you are, although I'll leave the ball in your court to determine where you really think you are exactly. Just notice that there's no circumnavigating the next stage from where you really are currently. You need to go up through that next stage directly. And if you try and jump a stage, you'll just be a confused and frustrated version of the stage you're at right now. Because getting to the next one is always a logical evolution from where you are, an evolution that addresses the specific pitfalls of where you are. So trying to jump 2 stages or more at once is exactly the kind of egoic nonsense that guarantees you're going to move absolutely nowhere whatsoever. Anyway, final word. If you decide to retain this information and don't just throw it out and say that this model's stupid, try and use it for good. Like, don't use it to be an asshole. Because remember, if you're using it to judge other stages, that necessarily means you're not that developed either. So if I see anyone doing that in the comments, I'm going to print out a picture of this diagram, wrap it around a cricket bat and clobber you with it. Alright, that'll do. Good lord, this video was long. I feel like I've grown a beard throughout the course of this video. Thanks for watching till the end, everybody. Like and subscribe if you want. Thanks again to elite level channel member Thunderbolt22A10. I don't think I've ever seen him and Danny DeVito in the same room at the same time, and I'm beginning to suspect that something's up with that. Now I know what you're thinking, Zan, that's just a coincidence. But I think it might have to do more with the fact that I have no idea what this guy looks like. Anyway, big thanks to my other channel members too, and if you're still watching, feel free to join the channel. I've got a bunch of cool YouTube membership perks if you're into that kind of thing, and as always, I'll catch you in the next one. Over and out.
Hello everyone, we are halfway through the Symbolism Masterclass as I record this. It's been a wild ride. I'm really pushing people to their limit. I like to watch in the chat and see people's brains fizzle. People seem to be following. It's tough, but it's important stuff. And we thought we could post a little section from the Symbolism Masterclass in which I describe in more detail than I ever have before what it is that I mean by fractal symbolism or the fractal structure of reality, and especially how it relates to that weird and wonderful vision that Ezekiel has of the wheels within wheels within wheels in the chariot of the divine revelation. And so we thought this could be fun for you to realize and kind of see how deep it is we're going in the Symbolism Masterclass. You can still sign up, of course. We have 3 weeks left, but all the videos are available for those that sign up forever. Once you sign up, you have access to them because you will definitely want to rewatch these videos. People I know are saying, I need to rewatch this 2 or 3 times because there's a lot. It is very coherent, but it's like drinking from a fire hose. We still have 3 episodes left to record. So I hope that by the end, people will be, let's say, well-trained in symbolic visions. And so please enjoy.
This is Jonathan Pedro. Welcome to the symbolic world.
This symbolic structure is really amoral. And this is one of the most important things to understand about it. It's not, we talked a little bit about how the pyramid in the image on the dollar can be parasited, like that there can be a parasitic version of it. And this is true of all of this. Like, so all of these images, the idea of hierarchy, there can be false hierarchies, right? The image of a ladder, there can be false ladders. You can be taking a ladder that like going up the corporate hierarchy is actually not the same as the ladder of virtues. It is a real ladder that has all of this coherence to it, but it doesn't lead to the same place. If you're actually, it can be a dangerous ladder to climb because it can lead to more and more kind of pride and power, and that is really the image of the hierarchy that is off kilter, is this image of an idol, right, or the image of a false hierarchy, of a false truth that is ordering the world, and it's kind of like this demonic imagery, or like the dark mountain. And so this is what you see in the image of. You see this in the image of the statue of Nebuchadnezzar, right? So the image of the statue of Nebuchadnezzar has this powerful hierarchy in it, but it's represented as an idol, right? It's said that it has a head of gold, and that the head of gold is the origin, right? It's the first empire. And then it has a torso of silver, and that's an empire that's lower down on the hierarchy, and that is also lower, let's say, further in time. It has the hips of brass, the legs of iron, and the feet of clay, and the toes that are a mix of iron and clay, right? And so this is a perfectly coherent vision of a hierarchy, right? So gold, right? Gold in some ways is the less solid metal. It's the one that is most looks like light, right? It's shiny, it's reflective, it's precious because it's rare. It's more like, but it's also you can't make a sword out of gold. That's not possible. And as you move down the ladder, you can see that the metals are darker and darker, and are also more and more strong, right? They have that kind of stability as you move down, and they're more and more stable, more and more stronger and stronger, until you reach the last one. And then in the last one, you have the image of fragmentation, where you have mixture. You have the toes made of clay and of iron mixed together. So you have this powerful image of a hierarchy where it's actually an idol. It's like a false hierarchy. It's an image of civilization in its false hierarchy, but it's using the same type of symbolism that would be used in other contexts to describe an order of qualities, from the most precious at the top, right, that is also the less hard, to things that are less precious and harder until they become brittle, and until they become confused, and then they shatter. So you have this weird image of heaven and earth. And what's interesting is that this image is reflected. So now the negative aspect of the hierarchy, and then this image is reflected in the order of the tabernacle, right? And so the tabernacle has the same order, similar order, as the order that you see in the statue of Nebuchadnezzar, which is that gold is held just for the Holy of Holies, right? Which is the place on which the heavens come down onto the top of the structure, okay? And then there's silver that are made out of parts in the holy place and in the sanctuary, but gold is just for the Holy of Holies, the highest place of the sanctuary. And then after that, you have bronze is used in the outer court. So you have the bronze that is used out here, and then ultimately on the outside, you have the clay, right? You just have the dirt, you just have the dust of the ground that is outside and is not part of the sacred order, we could say. Okay. And so Kwame Owusu says, why is the Nebuchadnezzar statue a symbol of false hierarchy? Well, in the story of Daniel, it's represented also as an idol that is meant to be worshipped. And so the image, Daniel sees the story of Nebuchadnezzar in a dream, and he sees this statue that is above, and then it sees that there's a mountain that is next to it, and a stone comes from the mountain. It's really a good idea to understand the stone as being from the top. So a stone at the top of the mountain breaks off and then rolls down and then destroys the statue. So that's the dream of Nebuchadnezzar. And so you could understand that it is an image of a false hierarchy that gets set up.
and then that which comes from the holy mountain, from the top of the holy mountain, this stone that is actually uncut by men, which is only made by God, rolls down the mountain and then breaks the statue apart, right? So that image of the stone that of course it's an image of Christ, but you could understand it as something that is not artificial, the true nature, the true hierarchy manifesting itself and destroying the false hierarchy. So that image can be represented. It's represented in many places in Scripture, where you have the let's say the Israelites leaving Egypt, where they have a pharaoh and they have a whole civilization that is falsely aligned. It's very powerful, but it's falsely aligned. And then they go through, right? They leave that, and then they go up the mountain to receive the true revelation, right? And in that process, the Pharaoh's men get drowned in the sea. And so you can kind of see it's a similar idea, where it's like you have to destroy the evil hierarchy in order to build. So think about it like you have little hierarchies in you, like sins that are little hierarchies that order behavior towards purposes and that are evil purposes. And so you have to deconstruct those before you actually move up the path, right? And so it's just important to understand that. So the reason why I'm saying that is that gold is used in the Holy of Holies, and it's used to make idols. And so the question is, what does gold mean? And gold means, it depends in what story you're placing the gold. And so gold can be an image of the holiest thing dedicated to God, and gold can be like King Midas worshiping riches and turning everything into gold in a way that makes him have no body, right? So he's just a head, and because he's worshipped gold, he now cannot feed himself anymore. He no longer has access to his body. So you can see how the same image is used in different contexts in order to manifest the different purposes. Okay? Zach Mack says, depends is always a safe answer, but it doesn't depend on anything. It actually depends on the context. And the context, when I say that we use the word context, it means purpose, right? A context is defined by purpose. And so, money, how can I say this? It's like, I can give food to the poor, and I can do it in the right way. And I can also do it just to increase my stature and my pride. It's the same action. But because the purposes are different, then the same symbol, the same behavior will play a different role. And that's really important. That's why, like, you can totally have images with evil kings, and you can have images with good kings. You can have images with evil peasants, and you can have stories with good peasants. And it just depends on how you structure things in order to manifest the purpose of why you're putting that image in there in the first place. And this is super important, because if you don't understand that, it's like you'll never understand the stories in Scripture, because then you'll think something like, the snake represents the devil, because look at in Genesis 1. And then by the time you get to Jesus saying that he's the serpent in the desert, you're going to become very confused, and you're not going to be able to understand what the heck he's talking about, because I thought the serpent was evil, and I thought the serpent was the devil. And in fact, that's not the case. The serpent represents something far greater, represents something which has different manifestations depending on where it is, right? And that's true of everything, right? Everything is, the best way of understanding is that things have a place on this order of being, right? They have their place. And this is, obviously, we're just in the second class. We're going to go through all of this as we move forward. But that place can be aligned differently depending on the reason, right, of why they're put there. And so every level think about it this way, every level on the ladder of divine ascent that we saw earlier with the monks going up the ladder towards heaven, every step on that can be a step towards God, or it could be representing a distance from God. It could be represented you not being close to God and a place of falling off. But that's true of every single level. All of them can become a type of forgetting, because that is the relationship of the many to the one, is that the many to the one, the many if they remember their connection to the one, then the many becomes an image of glory, becomes an image of fullness. But if the many forget their connection to the one, then they become an image of fragmentation. They become an image of sin. They become an image of death, right? Because they're veering away from the purpose. But the same structure, the same things that you do can be one or the other. Another way of saying is that every virtue you can do in pride, and every virtue that you do in pride is actually it's a kind of sinning, because you're using the virtue to increase yourself, and you're building an idol. You're building a little Nebuchadnezzar statue, which looks really good, but ultimately is not connected to the highest purpose. All right. So Luis Blanco said the snake is still a symbol of sin. We'll see about that. We'll get to that. And we'll see if that the serpent is just an image of sin. All right. Okay. Now, we just looked at the tabernacle, and we kind of saw how the tabernacle represents this mountain again. Right. So the image of the tabernacle, right, even though it's represented horizontally, it's still structured kind of vertically. So it has this hierarchy which moves from the outside into the inside, from the many that are there in the tabernacle. So you have all these people coming in, right, to the priestly caste that are fewer, to the high priest that is one, that moves into the place where the glory of God descends down on it, in the same way that Moses receives the law that comes down from heaven. So when Moses goes up the mountain, he goes up with the 70, and then he drops them on his way up, and then he goes up with Joshua, and I forget the name of the other person, and then Aaron, and then he lets Joshua and Aaron remain at a different level, and then he ends up alone at the very top, where he receives the law from heaven. That is the kind of the structure. And so this structure can appear, of course, as the kind of mountain, but it can also appear horizontally as, right, a kind of concentric structure, right? So you can understand now, if you look at the way that the camp of the Israelites is set up, that the place where heaven and earth meet is in the tabernacle, right? And then what that does is it radiates out, and it gathers all of the tribes together, right? So this is the camp of the Israelites. You have all the different tribes that are named around the edge, and in the middle you have the Levites that are in the center, and then in the middle of that you have the actual tabernacle, that is the place where God reveals himself. And so you have this kind of concentric model now, where heaven comes down from above and then manifests itself horizontally as this extension. And so that's why you can also represent heaven and earth this way. Right? You can represent heaven as the middle and earth as the edge. Or at least you could, heaven in the sense of the image of heaven on earth appears as the center, right? We use it in common parlance all the time, right? We say it's the center, it's the central thing, it's the reason why we're doing things. Like all of these aspects are completely coherent in terms of the symbolism, right? And that's why the image of the wheel is one of the images that represents this so powerfully, because a wheel is exactly the image of, you could say, a way in which all the multiplicity, right? So all of these multiple aspects are joined in and joined by the center, right? So the center is collecting all the multiplicity into itself. It's giving it its direction, is giving it its purpose. And in the wheel, it's particularly true and particularly interesting, because when a wheel is turning, the actual axis, like the actual axis of the wheel, the place around which the wheel is actually turning is a virtual point. It actually doesn't have extension. It doesn't have extension in space. It's just like a virtual point in the middle, and then all the multiplicity is turning around that virtual point. And so there's like you could say there are different reasons of why to represent the purpose or the heaven or the reason as the top of something, at the top of the ladder, the head, or as the heart, right? As the middle. And there's a distinction between the two, right? You could think of the heart tends to emphasize more the place where heaven and earth meet, but ultimately they play very similar roles. Like they play very similar roles in practice, right? And so sometimes there's a reason to distinguish them, and we can look at those at some point, but they play distinguishing roles, and they kind of compete, like in a way, like they kind of compete in different ways of representing it. So a good example of, not that they compete, but that they kind of alternate. So a good example of a place where they alternate is of course in Dante. Like in Dante, he is joining this imagery of a kind of concentric world and a mountain, right? And this is also where you can start to understand the yin yang symbol a little more. This is going to get a little esoteric because until now I've represented heaven as a point, right? I've said heaven is a point. It's things that culminate to each other, but that's really, you could say, where heaven appears, because it's the place where things meet. And when heaven manifests itself, it always manifests itself as a point. But you can also represent heaven as an expanse, of actualities, like as an expanse of names, right? An infinite, like, opening up. And then it's only when it comes down onto the world that it manifests itself as a point. This is where the image of the Trinity becomes relevant, where it's like we don't actually believe that the world culminates just into one, that it is in some ways there's an expansive element to that one, to that unity, which is beyond the unity itself. And in Dante, he's always trying to represent this. And so basically, he represents both, in some ways, the idea that God is the center, but that also God is also kind of surrounding all of us. And so God appears in your heart, but the truth of it is that you are in God, right? So that's when symbolism goes very, very, very subtle. Usually, most of the time when I talk about it, I'm always talking about the point and the center and how things kind of culminate into one. But this is supposed to be the masterclass, folks. And so you have to be able to kind of expand your mind and understand that ultimately the truth of it is that it's a point and a center, but we are also, you could say, in God. And that's why some representations will look different. And this is why in Dante, he plays with that. So on the one hand, he makes these mountains that you're constantly ascending in order to kind of go up. But he represents the heaven as this thing in which we're contained. And then once he gets to the very, very top of the heavens, then once again, God appears as these kind of concentric circles that are moving into one. She's constantly playing with you and trying to help you understand that God appears as this point of light, but that ultimately we are in God, right? So this accounts more for this imagery, right? This is probably the first time that I've even talked about this, which is that's why the tree looks the way it does, is that the tree has a central axis, which is like this connection between heaven and earth. And below it has all this multiplicity that is the roots that kind of connect it to the earth and distribute it in the earth. But then when you reach the top of the trunk, it opens up and has all of these stars all above, like all of this kind of all of this multiplicity of actuality that is up in the heavens, right? And that's what accounts also for this image of the Star of David, or the Seal of Solomon, which is that in this image, heaven, right, is this one. Heaven is this triangle that's coming down. So a way of understanding it that makes sense is to understand that as Moses goes up the mountain and he reaches the top of the mountain, and then he encounters God. You can imagine that encounter as being like a triangle that goes up like that, right? A triangle that goes up into the infinite and then comes down and points itself, right, to manifest as this center, as this seed, as this, as this pearl, as this, all of these images that we have in scripture of the center, and then redistributes itself into the earth as this kind of redistributes itself into potentiality, okay? And then that which is at the bottom is like the water, and the food comes up, right? And then becomes the fruits, all the fruits that are up above. And so this is really like the most subtle version of symbolism you'll hear about. Like I said, I usually don't go this far in my presentation, because for some people this could be confusing. And so now we're back to this. Like, this is what also accounts for this, the structure of this symbol, which is that both heaven and earth are in each other, in the sense that, right, heaven has to be in earth in order to activate its potential, right, towards the purpose. But earth also has to be in heaven so that heaven can distribute itself, right, and can be motivated to act towards potentiality. And so this can really help you kind of understand, I hope can kind of help you understand the ascension to some extent, and why the ascension is necessary in the image, in the story of Christianity, which is that the ascension is the continuation of the incarnation. Christ coming down into the world and manifesting himself in the world is, if you think of it in terms of metaphysical structure, it's simultaneous to him going up, taking man up into heaven. And that those two, Christ incarnate in the world and Christ's body up in the heaven, that is the ultimate structure, right? That is the ultimate structure of reality. And the yin yang is actually one of the most like successful images that manifest that, right? Of this double, this double being inside each other in a different way. And as we move forward in the class, we'll see the difference between the way in which the man is in the woman and the way in which the woman is in the man. Will show how what is the difference between the way in which, for example, you'll hear, because often when you hear like people talk about symbolism, they'll say things, simple things, and they're not wrong. They'll say the masculine is active and the feminine is passive. And it's like, anybody who's paid attention to reality knows that that's not the case. At least, like, what are you talking about? It's like, so the masculine is active and the feminine is passive. And then you realize, well, actually, no, the feminine is active, right? The feminine is doing all the things. And the man is passive because he's giving, or the king is passive, right? Because he's giving the orders. And the people are doing the things. So what's active, what's passive? And it just really depends on how from what perspective you're looking at it, and how you're seeing what in what, and we'll distinguish all this. Like, you'll see, it'll make sense. But I wanted to kind of take you on a limb and push you a little bit. There's no way we're getting to the end of this presentation today. It's just absolutely no way. All right. Okay, but let's get back to the wheel, because the wheel is an important image to kind of understand this. So we have this beautiful quote from St. Nicodemus of the Holy Mountain. He says, "We must therefore keep in mind that as the center of a wagon wheel has a certain number of spokes going out to the circumference of the circle, and so returning to the center where they meet, so also is the heart of man, like a center where all the senses, all the powers of the body, and all the activities of the soul are united. All right. And so Saint Nicodemus is talking about this image of the wheel as an image of the relationship of the heart to the externalities of the person, of the heart to your senses, to your being. And so that's why you can have all this type of imagery that is represented, you could say, as radiation, image of radiation from a center. And many religious images have that structure. And that's why it's important to understand it, because if you want to be able to know why sometimes you represent the relationship of Christ to the world like this, right? Instead of Christ at the top of the mountain, like you can totally understand how now it makes complete sense, because Christ is the center of the cosmos, and around him are the 12, right? The 12 tribes, the 12 signs of the zodiac, the extension of his rule and his identity in the world. Okay, but this is again, this is a universal image. I think that it takes its highest form in Christianity, but you will see it manifested in every single culture. So the symbolism of the wheel, obviously, some of you will know this. This is the what is it called? The wheel of karma, which is this idea of the Buddhist wheel with the way in the center, and then the eightfold path of the Buddha, moving away from the central vision of enlightenment into the practices that people are supposed to embody in order to reach the center of the wheel. But it's there in it's just everywhere. Here are a few examples. You have, this is the native medicine wheel, which is this wheel that is separated into 4, right? And the 4 are joined together in the center of the wheel. Obviously, you see people making mandalas. Everybody loves mandalas today because the mandala has the same structure.